Testing the audio for the live stream. Hey, good morning, everyone. I'm Sarah from Flashbots, and thanks for joining us for the MEV workshop at SBC 24. We're going to get started today. Our first session is privacy-enabled MEV solutions, and our first speaker will be Elaine Shi.
Put it on full screen. Test. Is the microphone?
Sound like it's on.
Oh. Hello. Can you hear me in the back?
It might just not be picked up.
Oh. It's on. Okay. I think you should adjust it too. Thank you. So I'm very excited to be here. Today I will talk about the story of ORAM and how it evolved from theory to large-scale deployment. So I co-founded a small startup company. We are called Oblivious Labs, and we are developing open source for Oblivious algorithms. And basically, if you are interested, you may want to take a look at our GitHub open source project. This is our logo. It's like the lock is like O, and this is O Labs, right? The O and with the L inside, but it's also a lock, so it's very secure. Okay. Wait. The clicker, hold on. I just have to use the iPad. Clicker doesn't seem to work. Okay. So first, I will tell you what ORAM is. Maybe many of you are already familiar with ORAM, but for those who aren't familiar, don't worry. I will tell you what ORAM is. And in fact, I will motivate ORAM with a non-blockchain example. I will actually talk about signals deployment. And then we will try to construct an ORAM scheme together. It turns out ORAM schemes, they're not like heavyweight crypto. They're just like simple data structures. So hopefully I can explain to you exactly how ORAM works in this short talk. And at the very end, I will talk about some more applications and what our company has been working on. So it doesn't work? Okay. So let's see why Signal wants ORAM. So Signal is this encrypted messenger app, right? So if you install Signal will ask you to upload your address book, and with the goal of finding your friends. So basically, let's say Andrew uploads his address book, and Signal finds out his friends and connects Andrew with his friends. But the problem is you might be worried about the secrecy of your contacts, so you may not want to share it with the server. Okay, so as we know, Signal wants to offer privacy, right? And here's a strawman solution. How does it work? Imagine the Signal server has some trusted hardware like Intel SGX. And this trusted hardware is going to create a hardware sandbox. Everything is encrypted, like your query, the answers, they're all encrypted. The data stored on disk is also encrypted. And the only place where things get decrypted is inside this hardware enclave. Because inside the sandbox, there is a secret key. You can decrypt things, you can compute on them, you can compute the answers. So it may seem like this gives you all the security you need because it protects the data contents. But actually, if you think about it a little bit more, for this particular application, if you only encrypt, really there is very little privacy. And the reason is because if the server can observe which records are being fetched, so you have the server is hosting this large encrypted database on disk, and the enclave has very small memory, right? So when the enclave wants to fetch some friend's entry from this large database, it needs to contact the operating system. So it will tell the operating system, hey, go get this page for me. So which means the server can directly observe which memory pages or which records are being fetched. And this leaks precisely who your friends are. Okay, so the point being that if you only encrypt for this kind of application, there is very little privacy. And this is the reason why you may want ORAM. So I'll tell you how ORAM works, what ORAM does and how ORAM works later. But actually here's another, this is a blockchain example. So let's look at Flashbot's use case. So as you may be aware, in blockchains, a big problem is called minor extractable value, or MEV. And this is also, why you are here today. And we want to build something called private order flow, meaning ideally when you submit your transactions, the block builders, the intermediaries, they cannot see the transactions until the block is built. So imagine a pipeline like this, like the users will encrypt their transactions. And let's say on the block builder, they're running a hardware enclave, or TEE. So all the transactions will be encrypted, and then you are building the blocks inside this SGX, secure hardware enclave. And the same problem here happens because when you build the block, you have to execute the smart contracts on the transactions. And as the smart contracts execute, you have to access data that lives on the blockchain. Like you may access, the crypto asset you are trading, like let's say Uniswap. You may access the sender and recipient accounts. And if you think about it, the locations you access are precisely the kind of information you want to hide, which means if you only encrypt things, also in this case, if you leak all the access patterns, there basically is very little privacy in this application too. Okay, so here we also need ORAM. And the question ORAM solves is following. So can we provably hide access pattern, but without too much cost? Okay, so let's go back to Signal story. The first solution they came up with is just like simple linear scan. So this is a naive solution. Let's say with every query, I will scan the whole database to find the answer. And of course, this doesn't leak my intention because the server cannot see which entry is matched. The drawback being this is hugely expensive. Signal's database has more than 1 billion records, right? So in some sense, this is kind of silly. I mean, they improved it slightly. They are using batched linear scan, which means they make a single linear scan and serve a batch of requests within this single scan. The overhead is linear, where n is the database size and beta is the batch size. And because it's so expensive, back then they needed 500 servers to serve all the load. So now we are in, we're in 2024 now, but in 2022, Signal realized, maybe we don't want to use the linear scan solution, and instead they implemented ORAM. And more specifically, they implemented Path ORAM, which is a scheme that we published back in 2013. So actually, Hilbert, who's in the audience, is also a co-author of the journal version of the paper. He helped us improve the proofs. So with Path ORAM, from linear overhead, we can get down to log squared overhead. And even though theoretically it's log squared, I want to mention these two logs are not equal. Like one of them has base 2, and the other has a very large base. So the log with the very large base is really like 2 or 3 in practice. So really, Path ORAM behaves like log n in practice rather than log n squared. And with Path ORAM, they cut from 500 servers to 6 servers, so they save like 100x in their operating costs. Okay, so at this moment, I hope I've motivated why we need ORAM, and we can try to together construct an ORAM scheme together. And before that, let me just quickly explain what ORAM is. So ORAM was first invented by Goldrick Ostrovsky back in the 1980s. But back then, the schemes were theoretical. They were not practical at all. So ORAM is an algorithmic technique that lets you provably hide access patterns, and the security is as strong as encryption. Like basically nothing is leaked. And behind the scene, what is going on is that you are permuting the data blocks in memory and you keep shuffling them as you access the data. So we'll see a scheme that solves this problem. And this is kind of the abstraction. Like if you think of ORAM as a box, the inputs are the logical requests, and every logical request is either I want to read some logical address or I want to write to some logical address. And it will translate each logical request into a bunch of physical axes. Okay, so the overhead is like if, let's say, one logical request gets translated in this case to 5 physical accesses, we say the overhead is 5. The security requires that no matter what your the input logical requests are, the output, the physical accesses should be indistinguishable. Okay. So in other words, by observing the physical accesses, you cannot infer anything about the logical requests. So if you were to implement ORAM in enclave, ORAM will actually be running inside the enclave. So it's like part of the trusted computing base. Okay. So how do we construct ORAM? We can first think about a strawman scheme. Like the most natural idea is we are going to permute all the blocks in memory. And the benefit of this is like, let's say if I want to access logical address 9, then I would end up going to a random location. And because let's say the adversary doesn't know this permutation, like to the adversary, I'm just like accessing random locations. So it may seem like this gives you some security. Indeed, it does give you some kind of security, but unfortunately, what you get is only one-time security, meaning that if you access every block only once, then it's fine, it's secure, because every access will just go to a random distinct address. However, in most scenarios, like you are not going to access each block only once. So suppose you access the block 9 twice, then you are going to go back to the same location twice. And this will leak statistical information like frequency, co-occurrence, and then you can do statistical inference attack. So therefore, if you just permute upfront, then the scheme is not secure. For the same reason why deterministic encryption is not secure. You may know that for an encryption scheme to be secure, it has to be randomized, and it's for the same reason. Okay, so the lesson we learned from this strawman attempt is that the blocks have to move around. And in fact, they have to move around. Like once I access a block, I have to move around immediately, because otherwise, if that block stayed in the same place, the next time I access it, I will just go back to the same location, and some statistical information is leaked, like some linkability information is leaked. Okay, so basically, this is the intuition, and we can keep this intuition in mind as we see the actual construction. So as I already mentioned to you, the construction is like, it's actually very simple. It's just a binary tree data structure. Every node in the tree is called a bucket, and a bucket has a finite number of slots. And so for today's talk, you can assume every bucket has 4 slots. Every bucket can store every slot can either store a real block or a filler block. So a real block is encryption of real data, and the filler block is just encryption of 0. And the filler blocks are there only for security. Okay, so, but by the way, throughout, I will assume all the blocks are encrypted. So the only thing the adversary can see is access patterns. And whenever you read a block, you're always going to re-encrypt it and write it back. And if you want to update the block, you just re-encrypt the new content. Otherwise, you re-encrypt the same content and write it back. So the server cannot see whether the blocks are being updated or not. Like the server cannot tell whether you are reading the block or you are writing the block. Okay. The most important invariant is that every block is going to be mapped to a random path. So imagine I have some block X and it's mapped to the blue path. Okay. In the beginning, I will cheat a little bit and assume the CPU stores a large position map that records where each block is. Okay, but in the end, I will get rid of this position map. So don't worry, like if you think the position map is too big, it doesn't fit in the CPU's cache, then just don't worry about it. I'll get rid of it in the end. So now reading a block is very simple. If I want to read the block X, I will read the position map, discover that X is on the blue path, and then I'm going to read every location on the blue path. I'm guaranteed to find the block X. So the most interesting thing happens after I read X. Because as I said, the block has to be relocated immediately after I read it. So how do I relocate it? Most natural idea, again, is I want to pick a new path and assign X to the new path. So suppose the new path I pick is the green path. So how do I write block X to the green path? This is the tricky part. I mean, of course, I have to update the position map to reflect that. But the next thing I want to do is to actually write the block to the green path. So where on the path can I write it? Can I write it directly into the leaf? Yes or no? Yes, it is dangerous. You're right. Okay, so it sounds dangerous and it is dangerous. And why is it dangerous? It's because if I write it directly to the leaf, I disclose the choice of the new path. So imagine the next request is for the same block. Then I would end up going back to the green path, right? So the server can see, oh, you wrote something to the green path and now you're accessing it again. Likely you're accessing the same block. So this is not okay because this discloses the choice of the path. For the same reason, you don't want to write to any of these internal nodes because all of them will leak some partial information about the choice of the new path. So what we want to do is to write it to the green path without leaking what is my choice of new path. So the only place that is safe is the root bucket. I can always write it into the root because the root is on every path. It doesn't disclose what is the choice of the new path. I mean, of course, there is a problem. I cannot keep writing things into the root because it will become full very quickly. I'll deal with that problem. But at this moment, I want to say the security of the scheme, like suppose we don't have the overflow problem, then the security of the scheme is trivial to prove. And because every request, I will just access a random path, and the choice of the path has not been disclosed before, right? And the only problem that's left to solve is I cannot keep doing this because the root will become full. So I have to deal with the overflow problem. So in fact, actually, okay, I lied a little bit. There are actually two remaining problems to solve. One is to overcome this overflow problem, and the other is to just remove the position map, which I promised you earlier. So let's do them one by one. I will do this really quickly. The overflow will be solved by a maintenance process called eviction. And the eviction, basically, the goal is to move the blocks towards the leaves to avoid overflow. And the question is, how do we design this eviction process? Like, there are two conflicting goals. One is, like, I don't want to spend too much work. If I spend a lot of work doing the eviction, the cost when amortized to each request will be too high. So I want to keep the cost low. But on the other hand, I don't want to spend too little work. If I spend too little work, then it's not enough to avoid overflow. Okay. And I will talk about the eviction algorithm of path ORAM, which is the algorithm signal deployed. So path ORAM's idea is I will just evict on the read path, the path which I have just read to fetch my block. Because like I'm touching this path anyway, I might as well do some maintenance work on this path. And how do I evict on this path? I will use the most aggressive eviction strategy possible, which means, so imagine I just grab the whole path into the enclave, and I will repack the blocks on the path. I will move things as close to the leaves as possible, subject to the path invariant. So that's it. If you put everything together, this is the path ORAM algorithm. I mean, except that I still need to get rid of the position map. But this is super easy because the solution is just one word. It's recursion. So how do we get rid of the position map? The position map is linear in size, but it's smaller than the original database. So I will basically store the position map in a smaller ORAM, and then I get a position map of the position map, and then I just keep recursing until the position map is constant size. At this moment, I can store it in my CPU cache. So the depth of the recursion is at most logarithmic because every time I can shave at least a constant factor. In practice, the step is just 2 or 3. So this is the log that has a large base, right? So remember I said the overhead is log squared. One of the logs comes from the height of the tree, and the other comes from the recursion. And for the height of the tree, that log is like really log base 2. But this log has a large base because in practice, the block size is like 4 KB. You can pack many position identifiers in the block, and the recursion depth is just like 2 or 3 in practice. So basically, this is path ORAM. The scheme is extremely simple. 16 lines of pseudocode. even if we count lines like endif and end4. It's so simple, you can print it on a t-shirt. Okay, just quickly summarize. This is tree-based ORAM. Every block is mapped to a random path in the tree. The most important is the block must relocate immediately after I access the block. And importantly, it has to be relocated without revealing the choice of the new path. The security proof is trivial. Like, I didn't talk about the proof, but the most challenging part of the proof is actually analyzing the stochastic process and showing that there is no overflow except with negligible probability. Okay, so I will just very quickly mention what our company has been working on, and maybe before that, let me just quickly mention some of the other applications of ORAM in the blockchain space, right? So I quickly mentioned the Flashbots use case in the beginning, but ORAM can also be used for privacy-preserving smart contracts and transactions. And we also want to build an oblivious data access layer for blockchain, right? So this is kind of like a database that hosts the blockchain data. But if like you are a wallet exchange, you are a relay, you want to access this database, we can completely protect your intentions. Like basically, our service will not be able to see which locations you are accessing. Okay, we have an open source release. If you are interested, you can go to this URL to check it out. And so I want to mention something about performance. So as I said, this is like not heavyweight cryptography. It's just a simple binary tree data structure. So the overhead is very, very low. There's almost no overhead. If you are running ORAM on an Ethereum-sized database, our latency is only like 20 to 50 microseconds, right? I stress it's microseconds, not even milliseconds. So this is like extremely fast. Yeah, I also want to mention like there are many applications that may be latency critical, like in Flashbots use case, because the block builders are going to be running this. So they really actually, they do care about the latency a lot. So this is why, you know, I mean, I think with like 20 to 50 microseconds, chances are like ORAM is not the bottleneck. Like it's like other parts of the system, like, you know, when your SGX is signing, that's on the order of milliseconds, I would guess. So this is unlikely going to be the bottleneck in the whole system. Our company also wants to build oblivious STL, right? So right now, the open source release, if you go to the webpage, it contains an oblivious key value star, which is the abstraction that Signal uses. It's also like the same abstraction for most of the blockchain applications. So what's the purpose of the oblivious STL? So oblivious STL is an oblivious counterpart of the standard, you know, maybe if you are familiar with C++ STL, you can think of it as a oblivious counterpart of that. And the point being that if you want to run some of these common algorithms like data structures, map, set, priority queue, range query data structure, you know, sorting, shuffling, if you want to run common graph algorithms, the best way may not be to take your non-private algorithm and compile it directly with ORAM. Because oftentimes, if you can design customized oblivious algorithms for these tasks, you can save even additional log n factor. So you can be even faster. So the point of the oblivious STL is we are going to provide a library with like these fast, customized oblivious algorithms and just make it available for people to use. So this just got started, and there's a lot of work remaining to be done. I also want to mention today, I really mostly focused on ORAM together with trusted hardware. But ORAM is not just for trusted hardware. Like it's also needed for scaling things like multi-party computation and fully homomorphic encryption to big data. So today, when we talk about multi-party computation and FHE, these primitives are used for small data. And the reason being, if you want to access some memory location, like with MPC and FHE, you would build a circuit to implement this memory access, and the cost is linear. Like essentially, you are making a linear scan in the circuit. And this is not going to go very far, right? Like as I told you, like with Signal, they cannot even afford to make a linear scan in clear text, but this is like making a linear scan inside the FHE and MPC. So if you want to get rid of this linear memory access overhead, it's the same. You need to have ORAM-based MPC and ORAM-based FHE. So in the medium term. And we also want to build practical techniques for like ORAM-based MPC and FHE. And we want to develop programming language techniques to help programmers develop oblivious algorithms. Like for instance, we can use compilers and type system to not only help us make sure our implementations are indeed oblivious programmatically, but we can also make optimizing compilers that take a look at your source code, and the compiler can intelligently figure out, oh, for this part of the code, you need ORAM, but for this other part of the code, your accesses are safe to reveal, so you don't need ORAM for these arrays. Okay, so this is our company's vision and agenda. So just to wrap up, do you need an ORAM? If you are doing encrypted computation on big data, chances are, no matter with trusted hardware or MPC, chances are you need ORAM. And if you come to Pittsburgh, you'll notice that in many of the coffee shops, they carry this ORAM donut. It's delicious. So if you come to Pittsburgh, I will buy you an ORAM. Thank you. Yeah, this is a quick plug. Like I have some lecture notes on oblivious computation and private information retrieval. And again, this is like our company's open source repository. Thank you.
Any questions? We can take about 2. Yeah. I won't go on the recording if you.
Maybe that's better. Hi, Professor. Thanks for the talk. I was just curious, what determines the size of the blocks in your tree structure? Is that just the size of a memory page, or?
Are you asking what is a block? Yeah, I guess block is like, I'm assuming block is the atomic unit of access. So for the case of SGX, indeed, it is a memory page.
Okay.
From the perspective, like if you are worried about the operating system, right? Like basically you are fetching, whenever you need to do a page swap, you need to go to the operating system and say, oh, hey, give me this page. So there, the block size is the page size. It's like 4 KB.
Okay, thank you. And then an unrelated question, but since I have the mic. I understand this probably doesn't apply to the MPC FHE case necessarily, but at least in the TE case, there's this alternative approach you can take where the access patterns themselves do reveal information, but you try to block all the channels through which the access patterns leak. So if you have a TE structure where the operating system or untrusted code doesn't have access to the access patterns, and maybe you protect the memory bus if you want physical attackers to be protected against as well. Do you think that's a reasonable approach, I guess more on the hardware level?
I think this would require a change to the underlying architecture, because today, like, if your data is living on disk, and if you want to fetch the data from disk to memory, you need to make a page swap, and the operating system needs to help you with that. If you modify the underlying architecture, it might be possible to like, one way is like, for instance, Intel could just implement ORAM in their CPU, and then the software doesn't have to worry about it. And actually, this is exactly why people were interested in ORAM in the first place. Like back in the 1980s, when architects were designing secure processors. So like today's Intel SGX, like in the research community, it was like first being researched in 1980s. And back then, when they were designing the secure processors, they actually wanted ORAM. It's just like there was no scheme practical, so they knowingly like left it as a leaky channel. But actually, a group at MIT, Srini Davidis and his students, like they actually taped out a secure processor running ORAM inside the CPU. So in this case, you don't need to do it at the software level. It's like done in the hardware itself.
Okay, thank you.
Which is maybe what you mean by like a protected memory bus.
Yeah, I guess there's multiple ways of protecting a memory bus, right? But yeah, that answers my question. Thank you.
Thank you. Yeah.
All right, let's thank Professor Shi. And we have a small change to the speaker ordering. Jonathan, are you ready to present? Thank you. Morning. Okay, so next up we will have Jonathan Passerat-Pongbach, who is a researcher at both Flashbots and Imperial College London. And he's going to talk about programmable privacy and MEV.
All right, everyone, good morning. Does this thing work? Yeah, I need to stick it a bit closer, I guess. Okay, so you might be familiar with this terminology of programmable privacy is getting traction. And recently at FCC, I realized that it was being mentioned, but like a few other similar terms were mentioned as well. So I was like, let's try and clarify these terms if we can. First of all, let's start with what do we mean by privacy, and in particular privacy at Flashbots. But first, a little detour in privacy in Web3. I think when we mean privacy in Web3, we've been very much driven by the idea of like ZK proofs, protecting transactions. So like this idea of shielded transaction, that's pretty much what people have meant for quite some time when they were talking about privacy. More recently, we've been like discussing private smart contracts and private mempools as well. So that's kind of like the IDs that are associated with privacy, and this emergence as well of co-processors, either powered by SGX, as we might see a bit later today, some as well powered by FHE. So all of these terms basically are a bit of a mixed bag when we talk about privacy, and it's not really clear what we mean. I think what's important though is that these primitives all are meant to unlock new use cases. And that's what we mean by privacy at Flashbot. It's not about providing privacy for the sake of privacy. It's more about what use cases can we unlock by introducing these privacy primitives. And in particular, how can we achieve like better features for our protocols? How we can remove trust in Flashbots as an entity within the ecosystem, for example, and increase the resilience of protocols. So in the short and medium term, this is very much anchored around TEs, and in particular like Intel's SGX and TDX. But that doesn't mean that this is the only thing we're exploring. There are multiple paths being explored, and in truth, there has been like at least like two prominent proposals for what we mean by privacy and programmable privacy in Flashbots. And one was or is actually MEV-Share, now like being like the engine behind Flashbots Protect. The idea here is that you give the user some form of control over what part of the transactions to reveal. So we're not talking about any cryptography or anything. We're talking about some kind of like selective disclosure of information here. And you can go from like the most private version, which only discloses the hash of the transaction, which is basically pretty much useless for a searcher, all the way down to exposing all the fields of the transaction, which help the searcher make more elaborate strategies on the transaction, but also release a lot more information about your trade. So it's about whether you're comfortable with that or not. It's a trade-off. Another approach, very different, is this track that we call a T builder. And here, the idea is to start, in a way, abstracting the services that we used to provide and wrap them into some more formal guarantees provided by these TEs. In particular, one aspect that is interesting beyond providing pre-trade privacy, because that's something we were offering in a way by social contract before, is this idea of like verifiability. So we start introducing like new features in this game, and in particular, users can verify that the refund rule in the builder has been applied correctly because it is run within TE, and thus they can rely on the traditional remote attestation based guarantees of the SGX/TDX stack to obtain like more formal guarantees on what's happening on their transactions. So just to summarize a bit what we've been talking about here, we've used the word privacy in a few different contexts, and I would say that the last one, for example, would qualify more as confidential computing, right? That's what we're doing when we're trying to embed SGX and TEs in the game. Also, all of these like secure and confidential doesn't equate private. So we'll talk a bit more about that later, but that's something to keep in mind. We also label MEV as like a programmable privacy approach because we're providing hints to the searcher, and we give some level of control to the user, but it's not really quantified. It's not really clear what kind of privacy guarantees we're giving here. And if you expand to like these cloud of words related to privacy that I was mentioning before, you quickly realize that there's a lot of terms that are being used these days. Some in the more Web2/academia land. Got privacy enhancing technologies, which is the one I think that has got the most traction overall. But we start to see, confidential computing is very attached to Intel and TEs. Secure computing, encrypted computing for the more software cryptography declination. And in Web3, we have programmable privacy, but we also started to talk about confidential DeFi and decentralized confidential computing. And my take is that we're all doing the same thing here, right? There's no magic there. And it's nice to have like these, memes that can gain some traction. But what's more interesting is to better understand the properties that these protocols, that these primitives are providing. And that's why I like to think about privacy enhancing technologies as like three different aspects. The technologies that are trying to protect what I call the input privacy. So really the privacy of the data that you inject in the computation. That's usually what we mean by confidentiality, right? That's where we are here. And you'll see that's one of the aspects that we are focusing a lot of time on for good reasons, but that's clearly the state of things today. There's like this other side of privacy, which is from what I've seen, like less of a concern, less of a focus at least, which is output privacy. And it's really about how much information does the result of a computation leak on the data you put into it in the first place. And usually that's something that we tackle with things like differential privacy, for example, where we can give some very formal guarantees about the level of information that is being disclosed. And the glue between these things tends to be around smart contracts and blockchains in general. You can even think about very fast bulletin chains that tend to be useful sometimes to make the bridge between the two. So that's what we're going to qualify as enforcing policy, so more the governance part of the privacy that allows users to have maybe a bit more control on the information they disclose. And the sad thing is that these things tend to be close here on this diagram, but we tend to study them a lot in isolation, whereas pets should really be combined to shine. And we'll see a few examples of what that means here. But most of these technologies are in isolation amazing, right? But they don't really provide an end-to-end solution. So instead of like talking about privacy-enhancing technologies, there is like another term that I think has been coined by Nigel Smart, which is, let's switch this acronym to partnership enabling technologies. So let's bring them together to make the most of them, but let's also use them to bring users together in joint computations. Okay, so let's just like double click on each of these topics to see what we mean by that. So FHE plus snarks, FHE plus ZKPs, for example, is very interesting in the sense that you'll see with a concrete example later, FHE by itself cannot really be deployed as a protocol, right? You need some training wheels in a way to make sure that the thing works. And in particular, we're very interested in this idea of like not necessarily verifying the whole computation first, because that's very challenging, but in particular validating the ciphertext that we inject in the computation. And the reason is, if you don't do that, if I can inject any invalid ciphertext in a decryption process, for example, in decryption oracle, there are some very simple attacks that allow you to gradually leak more and more entropy and eventually disclose the private key. So you really want to make sure that the ciphertext that you're getting into a decryption oracle, for example, are correct. They are well-formed ciphertext, and we use proofs for that. There's 2 instances of that. Zama is building one for TFHE in their Rust library, and PSE has recently put together a paper called Greco, where they do that for another scheme for BFV, I think. When pairing together FHE and TEs also makes sense, because FHE by itself, again, doesn't provide this verifiability. So maybe we can get that by relying on trusted execution environments and the remote attestation property. The idea here is that it's going to be way cheaper and way faster to obtain the integrity property from TEs. But it's also pretty fine in terms of assumptions, in the sense that even if you don't trust fully the TE, or even if the TE is breached for one reason or another, you don't lose everything, in the sense that you've got this, you still are protected from a confidentiality point of view by the encryption, right? So you lose the integrity, but you can still be confident that your data is not being leaked. So that's why it's important as well to have this distinction between input privacy, output privacy, and all of these things, instead of just having programmable privacy as a whole, I think. ZKPs plus TEs, something that we've seen over the past year or so, I think, is the emergence of multi-provers, right? So it's way cheaper, it's way faster to produce proofs, as in like remote attestation-based proofs, that can be an alternative to Snark for rollups, for example. And there's like a few projects that already offer these kind of services, so that's pretty interesting. But more importantly, that also can act as a training wheel for Snarks. Snarks are very complex protocols, and it's not completely ruled out that we can still find bugs in the implementation of some of them. So having the TE act as a fallback can be highly beneficial in this context. But also the other way round can be interesting to study, in the sense that if you just have a ZK proof, you don't really have any guarantees on the input privacy. You're assumed to be the prover to be the one controlling the data. So if I want to delegate proving, if I want to generate proofs for data that is sensitive, I either have to do that by myself on my laptop, or the only option I have is to trust the prover doing that on my behalf. So running a prover within a TE, for example, this time allows you to have to add the confidentiality guarantees on the data you're providing to the prover, and still obtain some verifiability guarantees from the proof. And it's kind of like going in circles and like, helping one another in the case of TEs and snarks, because once you've generated a proof that is based on TEs, for example, it is not the kind of proof that we use to verify on chain to unlock a next action in a smart contract. But the good thing is that you can also snark the attestation verification process. And the Automata team has done that, for example, for both SGX and TDX. So you can turn back the TE proof in a way into a snark if that's something that you find more appealing for your application. So another good highlight of like the combinations here. We've also seen ZKP and MPCs being brought together for quite some time. I thought it was just like an academic endeavor, this paper on collaborative snarks, but recently RenegadeFi has used it to power the dark pool. And the idea here is that you don't generate a proof by yourself anymore. You run an MPC protocol to inject like shares of a witness within the computation and spit out like a single proof out of it. So that's pretty interesting too. Okay, so giving you more concrete, a concrete instance of what do we mean by that. I've recently been working on a prototype to run a background arbitrage protocol using FHE. The idea was that we want to provide more formal guarantees in Protect, for example. So we want to go beyond offering like guarantees as an entity to more formal guarantees that are backed by cryptography, for example. So going towards more privacy by design, but retaining some level of programmability. And to that, we just like take a very simple setting where we focus on a single Uniswap V2 transaction swap, and we use FHE to represent the strategy that a searcher would run to backrun this transaction, for example. So I'll just skip the details on what is FHE. I think you might have an idea, and if you don't, I'm happy to talk about that later if you want. Just to give you an idea of the setting we're using, a single user encrypts their transaction and sends that to the searcher infrastructure. Here we assume that the searcher has like a large enough machine to run the computation, and the searcher injects some preferences, some parameters into this construction, and the output of this computation is an encrypted bundle, or at least an encrypted background transaction if the background was successful. The searcher has no ability to decrypt this transaction, right? So it's like a one-off computation, but it doesn't have any feedback on what's going on here. Everything goes to an assumed trusted builder that will decrypt and insert that into a block. So it's a highly unrealistic setting, of course, but just with this very simple setting, there is like a bunch of challenges that stand out, right? Of course, the computational overhead is still fairly large, and we might need some more bespoke optimizations to make this algorithm faster. But mostly, as you've seen, by using FHE as a standalone technique, we can't really provide any real-world guarantees here, right? We lack the integrity of the computation. We have other challenges that are pretty hard to perform in FHE, one being performing ECDSA signatures, for example, to actually finalize the background transaction. And we would need to also have some kind of public key that is controlled by a set of validators. So that would mean threshold FHE, but in itself is no silver bullet in the sense that we need guarantees on what the validators are doing with their shares. So luckily, Ts are pretty good at this. And I wanted to just like give you an idea of like what it would mean to turn this prototype into what could become like an FHE private mempool in a sense. So in order to do that, we need to lift these barriers that we've encountered. The signature barrier, for example, would be pretty hard to solve in pure FHE. CDSA is not very FHE friendly as a signature algorithm. So some ideas could be to inject some MPC in there and engage in a protocol with the builder, either sign the ciphertext and then do something with the builder to verify the signature before it's being decrypted, or maybe use a kind of abstraction to replace ECDSA altogether by a more FHE friendly signature scheme. So here we start to combine two confidentiality primitives to get to a new feature. The threshold decryption is something that in a way is more advanced, because like we start to see networks not in production yet, but at least being enhanced to provide FHE keys and FHE threshold decryption. And it turns out that they're already backed by enclaves. So in Zama's construction, for example, they rely on AWS Nitro, but there's nothing preventing them from running that into SGX. And to keep building in the defense in depth design, it might actually be desirable to rely on multiple different TEs. In case one is being breached, you can still rely on the others to complete the protocol, for example. Interestingly, we have not talked much about this output privacy thing that I was mentioning in the first place. And I think that's critical to making like these more interesting protocols become a reality. You might recall that searchers do not get any feedback from this design for now. And there's like a clear reason to that. We don't want to open what we call a covert channel, where the searcher could start to encode information by gradually requesting the service and trying to infer some information by doing that. So it's pretty hard to make sure that you close all of them. But the trade-off is that you reduce the programmability for the searcher. So for now, we kind of like guarded by the fact that the computation runs in a circuit. So we have some guarantees on what is being run. But in the ideal world, you would like more formal guarantees on when is being released and more programmability for the searcher. So that's something that would be more interesting in my opinion. And just to wrap up this presentation, I think just a few call for actions, call for collaborations. I think what stands out from the state of things today is that not all the elements of the programmable privacy stack are described thoroughly. And there's a recent effort in a paper by Andrew and colleagues on programmable privacy SOK, which is a great effort in this direction. But that's clearly the thing that we need to do more often. And I think one way to do that is to basically focus on like opening the black box of pets. And like, yes, it's great that we have memes like programmable privacy, but we need to be more precise on what we mean by privacy. And we need to not be afraid to open these black boxes and really study these methods and protocols, not in isolation anymore, but in combination for end-to-end solutions. In particular, we can learn, I think, a lot by building community tools and baselines for the common use case that we have identified, and then to better understand the impact of adding programmable privacy to these use cases like dark pools and batch auctions, for example. The questions that remain is that, as I said, we focused a lot on input privacy, right? We've been working a lot on FHE, we've been working on MPC, on ZK. We've been leaving out a little bit too much, in my opinion, the output privacy, which would be tremendously helpful in, for example, quantifying the amount of information leakage in covert channels, for example. It's not really clear what an attacker could do with these data being leaked. So that's something we really need to investigate further. And on the more TE-specific thing, I think by also opening the box of the TE itself and going more towards like open TEs, we can not only like learn more about the guarantees we're offering, but also get to a better state of like security overall. And you know, it's not crazy to think that we can see the same kind of like acceleration and development that we've seen in DK over the past 10 years if we all together focus on this aspect. And the last point I would like to mention is that, yes, all of that is not really about privacy for privacy. It's really about information control. And for that, we need to put the user at the center of the design and really always think about what is being input in the computation and what is being output by the computation and what leaks out of that. So thank you very much for listening. Just a few references to the things I've been mentioning. And if you have any questions, I'm happy to take them now or later at the break.
One or two questions. I'll ask you that. Any questions? Oh, goodness.
Thanks for the talk. So why do you think we don't see as much emphasis on output privacy in the industry? Is it that it's a harder problem, or is it less marketable, or like, you know, we just like you're saying, we see less of it?
I don't know if this one works. Okay, let's take the other one. I'll keep this one for now. I think that's a good point. Yes, I definitely think it's less marketable in the sense that it's mostly about providing stronger guarantees and not really unlocking use cases in this case, right? The new use case really comes from the input privacy. That's what allows you to enter applications you would not in the first place. And I think the other reason why this is maybe less studied, it's less generic in the sense that you need to study it for every single application, right? It's harder than for example, working on accelerating ZK or FHE, which is going to have an impact for the whole community. We have tools like differential privacy, but if you really want to apply them, it's not just about building the tools. It's really about making the analysis of your application. So it's more of an auditing process, like a security audit / proof process, rather than building tools in this direction, I think.
Okay, thanks.
All right, any other questions? All right, let's thank Jonathan.
The mic. Sure. Thank you. Is there something I have to hit? Yeah. All right.
Okay, and our next speaker will be Tarun Chitra. Tarun is the CEO at Gauntlet and an investor at Robot Ventures.
Hey, everyone. So, I think the previous talk did a lot about sort of the, I would say, some of the more concrete implementation questions around privacy and DeFi. This talk is going to be more about some of the theoretical type of problems and sort of what things that might be useful for solving them look like. So, modular privacy is a made-up term made up by me, but I feel like there's sort of this natural thing when you think about writing confidential DeFi applications, where there's sort of three very broad strokes types of state that you have. You have fully public state, you have statistically private state, so that's sort of something like differential privacy or something with some PIR type of retrieval mechanism, and then you have fully algebraically private. So when I say algebraically private, I mean T, FHE, potentially MPC. And one really important thing about writing these applications is you have to understand when you cross a state boundary. When I convert a private state into public state, clearly I've crossed a boundary. But maybe I have some private state that generated some output, and from the output you have some information about the private state from the public output. And understanding when you cross those boundaries is quite important. Another important thing about privacy is different levels of privacy lead to very varied composability guarantees. And one question is, how do you kind of blend these guarantees in a unified manner for users and developers? And I think we'll talk about how to think of this sort of in a more algebraic way. And finally, the last thing is confidential DeFi can only really succeed if it has any ability to be competitive pricing-wise with public DeFi. So, public DeFi is just so much cheaper, it's never going to work. So we're going to talk a little bit about that. And the only shill I will have is Malesh and I who's in the audience, have a paper on something related to resource pricing today. All right. So modular privacy. So the first axiom you should always remember is you really can't have fully private finance. Fundamentally, finance relies on selective disclosure for supply and demand to match. So you need some public state, right? You need a price, you need an interest rate, you need a fee. You need something that inherently has some notion of aggregating many people's information and constructing a public output. In the long run, users just won't utilize protocols that don't provide any public information. Now, I added this disclaimer that meme coins don't count because I needed to add the disclaimer given the post-Solana address send money meme coins, which for some reason have no public disclosure, unsurprisingly. But if you look at the general sort of literature within sort of the economic side of the world, a lot of things are based on selective disclosure, right? So like all of auction theory is based on some notion of how private my valuation for an item is. Do only I have a value for the item? Does my value depend on your value? Do our values interact with one another? But on the other hand, finance does partition private state. So there's a sense in which all transactions, and I don't just mean blockchain transactions, I mean outside real world touch grass transactions, can always be partitioned into sort of three rough states. One is fully public state. This is a government telling you a tax rate or a reserve rate or a public price. One is private state, individual balances of banks and users and entities. And the final is things that are public aggregations of private state. So this is things like LIBOR. These are indices. These are CPI indices. These are things where the inputs themselves are not fully public, but the output is public. Some aggregation, some function that takes in those inputs. One other thing about this talk is it's not going to be particularly formal, but it will talk a little bit about sort of a research direction that I have been kind of going on. So as a kind of disclaimer. Okay, so let's take the classic blockchain example. So, the easiest thing to analyze, constant function market makers, they're sort of, because they're the easiest, they're a nice testing ground. But of course, for generic applications, you will need more strength. But for CFMMs, a natural thing to note is they have a fully public pricing mechanism, and there's a very simple algorithm for figuring out how to invert the total balances from just knowing the trades or the prices. On the other hand, they're easy to make statistically private. So they're hard to make algebraically private because they disclose a price and you can always invert what people's trades were, but you can make them statistically private. So the first version of this, is a paper of mine from a few years ago, which shows sort of how to get differential privacy for these. The second version is actually a question of, well, if I wanted to be differentially private, how do I have to change the AMM? And this is a paper from last year from Goyal and Ramsar, which sort of shows there's a minimum amount of noise you have to add to the fees that users pay. So in order to get privacy, there has to be a randomization of either the fee or the price. And it turns out the minimum distortion is the fee. So again, this example shows you this notion of I have a public state, I have a price, I have statistically private state, which might be balances or might be some aggregation, and then maybe I have algebraically private, which is a single individual state. So, especially if you look at how people are trying to write private DeFi applications, in general, you do see people sort of crawling in the dark in their code bases, manually segregating things into these kind of three types, where there's this clearly public thing that everyone can call and read. There's this clearly statistically private thing that is an aggregation of a bunch of private state or indirectly leaks a bunch of private state. And then there's the algebraically private piece, which is what a T or FHE gives you. In a world where this were easy to write software for, you could imagine a library that handles boundary crossing. So like, hey, when I upconvert some private state to public state, I make sure that this only is encapsulated to some particular area. Or vice versa. If I have statistically private state that I want to make private, I have to add more noise before I put it in enclave. So this gets us to the natural question of what does composability look like for these kind of private actions. And the interesting thing is when I have fully public or fully private data, so fully public could be finance, fully private can't be finance in the sense of there's no public data for people to make an interaction against. Those are self-composable. Once I stay in the enclave and if I never leave, I'm fine. And if I'm always public, it's always fine. But the problem is, again, when we cross a boundary, we lose some composability. So the first sort of inklings of this are, when you look at differential privacy, your differential privacy worsens when you compose functions. Now, you can bound how much it worsens, but it definitely gets worse. And it gets worse in potentially a really bad way, depending on your calculation. But the important thing is statistical privacy has partial composability. Like, yes, if I compose two statistically private data sets, I might get a worse notion of privacy in the sense that someone only needs fewer data points to recover the input. But nevertheless, at least there's some partial composability. And the one thing I want to point out is there are many different results that are inequivalent for how this partial composability works. And so this in and of itself tells you that you can imagine that a developer who has to think about this would get extremely confused as to which one they're actually really using. So I think a lot of these composition theorems sort of suggest you should think about privacy in sort of this algebraic term, in these algebraic terms, which is you have fully private state, you can lift it, you can forget that you're fully private by adding some noise and get statistically private, or you could reveal it fully and you get public. And you could kind of think of this idea of like when I'm in one of these states, so when I'm fully private, I can do compositions that are fully private. When I'm fully statistically private, differentially private, I can do compositions and with some loss. When I'm fully public, I can do compositions like Ethereum today. But one real question is, what happens if I go to the right and then I go down? So I take some private state, I lift it to a differentially private state, and then I compose that state. How much worse is that guarantee than my initial state? And this is a natural question to ask, because this is a question of, well, if I knew the answer to that, I could make a compiler that takes in your code written as purely public state and figures out how to allocate to each of these groups. So one nice thing, if you think of it in this manner, is you get a sort of minimal lossiness guarantee. So this kind of view preserves your sort of information theoretic privacy within each category. But the other thing is it makes software development a lot easier. And I think that, in and of itself is probably one of the real reasons people don't write private software, write private DeFi, to Quintus's question earlier. Okay, the final thing that I want to kind of talk about a little bit is, okay, well, great. So now we know we have, we should be thinking about different types of privacy. We should be thinking about how the different types of privacy compose. And potentially, if we knew how to do that, we could make it much easier to do private DeFi. So in the long run, what properties do we really want from an economic perspective out of these protocols? You need some notion in which there's a amount of revelation that a user has to specify, how much state they publicly reveal to kind of get an outcome that they want. So how much do I have to reveal about how much liquidity I'm providing in a LP pool? Do I have to reveal to kind of get my fees optimized? On the other hand, you want to reduce efficiency due to increased privacy as minimally as possible. And so you sort of have this kind of natural minimax-like problem. And your goal is to kind of find a compromise between these two extremes. It's possible that there might not exist such a thing, but for CFMMs, we know that does exist, which is some suggestion that there are a set of DeFi protocols that would give you this property. The second thing is we want the welfare for all the users of the private version of the protocol to always be sort of some constant fraction of the public version. In some sense, that sort of says, hey, look, even though I'm going into the private mechanism, I'm only losing at most, 10% efficiency. I'm only getting a 10% worse price. And the final thing, which I think is something that's often missing in papers about private applications, is the user should be able to individually choose their desired level of privacy versus efficiency. I think in a world where the developer chooses for the user, it becomes a lot harder for the user to even reason about whether they value the privacy or not. And so you should have some way of tuning it. So something kind of been working on, and this is an extension of sort of the differential privacy for CFMMs is, well, actually, maybe you can formulate this as an optimization problem where I want to meet these three constraints, where I minimize how much state is revealed for a given level of efficiency. I also try to make sure the welfare sort of satisfies this competitive ratio bound. And the sovereignty piece is, some input the user can give to the optimization problem. All right, so this kind of thing, let's go through what this says step by step. So we have a function which measures our sort of notion of efficiency, and this takes in sort of the state that is revealed, as well as some hyperparameters theta, which you could think of as the user input. You could also think of that as constraints on the output that the protocol gives. These constraints can also be resource prices. So these can be things that are, how much am I willing to pay per unit of state that's revealed? Or in the TE context, how much am I willing to pay? If it costs me K times more to execute in TEs, maybe this data might be a budget. I'm only willing to spend a total amount of this of resource in this environment. X is a valid state of the protocol, so this could be your set of public balances, could be your set of reserves. Now, here's where we kind of get to ensuring that this welfare constraint holds, which is consider a notion of a projected state. So this is sort of your state that's fully private, and your sort of statistically private state. So you can imagine that there's some model in which you have a disclosure mechanism that projects some of your state to be fully private, some of it statistically private, and now measure the efficiency under those disclosure rules. So this is where a developer chooses P or SP. And finally, we have this function C. So if you remember here, I said that the welfare of the private protocol needs to be at least C times the public protocol. And the goal of solving this optimization program is the user could say, hey, I want C to be 10%. I'm only willing, I will take as much privacy as you can give me, measured in this way, but I don't want to be 10%. I don't want to be worse than 10%, more than 10% worse than the public mechanism. And the idea here is that this kind of trying to formulate this optimization problem allows you to take in user input while also allowing you to think through sort of some notion of this privacy versus efficiency trade-off. And you can formalize this, but this talk won't talk about that. So, a natural thing you might say is, well, hey, look, how do we price these resources? This is sort of a thing, I think, in pretty much every blockchain that has real users that people are facing every day and thinking about, which is, how much should blob space be? In Solana, it's how much should state contention cost? And so there's sort of a natural thing of like, well, how do we even price these public versus private resources? So a natural thing you could do is, again, formulate this optimization problem subject to some constraints. So these constraints in this case might say, hey, look, I am only willing to spend 20% more than the purely public gas cost. That's what the first constraint says. The second constraint says I'm only willing to lose up to 20% in efficiency. And then the third constraint is sort of like a security budget. Like I want at least K bits of privacy. And you know, how exactly how you measure that depends on how you define P and SP, but just as an illustration. So I think if you have a formulation like this, you might say, hey, well, who's solving the optimization problem? If the user has to solve it, we're dead on arrival. But if you look at the market right now, especially when you look at the off-chain actors and intent solving type of things, you could imagine that the solvers are actually solving this optimization problem on behalf of the users. So the users submit C. The users you could think of as submitting constraints. They submit the 0.8 and 1.2 and K here. And then the solvers try to return an optimal matching. And this would at least allow a way in which users don't really have to think about this optimization problem, but they're able to get some guarantees on the privacy versus utility trade-off they make. And that's it. And I'm shilling my paper again.
Any questions?
So you talked about these three general categories of privacy levels of data, and statistical privacy is a sort of variable category, and wanting to build software that uses these and presumably moves data between these explicitly. Do you think that techniques from programming language-based security, specifically information flow based techniques, can be useful here, or is this not amenable to that?
Yeah, for sure. So if you think about this like grading type of thing of like, hey, on the vertical lines, we're composable. On the horizontal lines, we're like lossy. You can basically try to take information flow type arguments and add in some lossiness factor, right? So like when I go from private state to differentially private and then I compose, do I have an information flow guarantee that bounds that, right? And so that's sort of what this is trying to get at, is that information flow is focused on kind of purely private, purely public, and like that boundary.
Well, usually you can have multiple levels of different security, and things can move to strictly more restrictive levels.
Yeah.
Public data is allowed to influence private data, and you can have various label structures as opposed to just two.
Yeah, that's true. I guess my main point is like, you know, if I think about these kind of what composability guarantees you have in differential privacy, you would need some way of picking which layers, you know, how tolerable each layer is as you move between them. And I think that's sort of the type of thing that people have done, like they've done, especially in mobile OSs, where there is actually some, you know, actual real usage of differential privacy. So like in the Google Android keyboard, they aggregate a lot of information, and that's how the recommendations are done. So that's an example of differentially private use case that has like a few hundred million users. And that, you know, in that case, they just spent many years tuning this. And there's like a million papers you'll find of like, how do you choose your epsilons? And I think the devil is definitely in the details of that. But I think the end user should dream of just a compiler where they don't have to think about that, right? Like they don't have to think about those transitions.
I just have a short comment, I guess it's related to Isaac. I guess, I'm happy that I'm not the only person who got reminded of information flow. So I actually forwarded you a paper called Viaduct, and I thought you might be interested. It's like exactly what Isaac is talking about. It has an information flow. You can like declassify certain information, so it allows like some kind of release. But there's a type system that makes sure like your privacy and integrity labels are internally consistent. We actually have a compiler. Like, I mean, the vision is you can just write the ideal functionality. And then the compiler will synthesize the cryptographic implementation for you. So it's a little bit like what you were saying towards
great.
the end. Yeah.
Well, then great.
I thought you might be interested. Yeah. Thank you.
Thanks.
I saw one more.
Since thank you for the talk, by the way, but since you're like the state is 100% composable at different layers of privacy, so like fully private is fully composable, fully public fully composable, does overall system welfare actually increase if you remove the user's ability to specify what level of privacy they want? For example, if you're running an auction in a trusted execution environment, the auction's more efficient if everything is in the enclave versus some being inside and some being outside.
Yeah, that's a good question. So a lot of that is in this kind of framing of this optimization problem. A lot of that is hidden in the definition of EFF and C, where it's like, well, I have some notion of efficiency per unit of state that could be, hidden in this. Is it just purely the read and write of the cell type of efficiency? Probably more like what Elaine was talking about earlier, or is it the execution efficiency? Like in the case of a CFMM, you have this huge blow up in complexity for evaluating how to execute the trade if you add per unit noise. So that's where the devil's in the details. But I think the nice thing about AMMs is like they're very simple, so you can write out this optimization problem for them and get a closed form solution. I think for other programs, like for lending protocols and stuff, you have to be much more careful about that delineation because the security properties of those systems will change quite a bit. Whereas AMMs, it's like, okay, I got a worse price, but I don't immediately like lose all my money in the same way as a liquidation. So there's kind of something you have to be a little bit careful of. But yeah, definitely, there is, this is a stylized view. For each kind of program, you need to think about an optimization problem like this.
Got it. Thank you.
All right, let's take one more.
Hi, thank you for the talk. In hardware security, there's this concept called microarchitectural leakage descriptors. So you take a hardware performance optimization, and then you can essentially create a model of what information is leaked given a given optimization. So it's like a formal way of categorizing like information leakage through side channels. I'm wondering, is there an equivalent like formal way of describing the efficiency versus like privacy trade-off in terms of a given way of doing a market maker?
Yeah, so for the AMMs, there's definitely, like, between these two papers, I think they explicitly kind of write out this sort of information loss in terms of like number of bits of the price that you can recover per number of bits of knowledge, number of bits of the trade that you can recover, given a certain number of bits of the prices you see. So you can think of it as like a transfer function of like, I have this much entropy input, I have this much entropy output. So it looks like kind of these bottleneck type things, except I think you're not really explicitly trying to minimize those because that'll be sort of NP hard, and you kind of minimize some surrogate. And because all these CFMs are convex, the convex surrogate has the same answer as the NP problem, which is like why we kind of can get these results. For more generic functions, it's harder, right? Like you will run into your natural, can I solve an approximation algorithm? Because like there's no way to solve the exact optimization minimum. But yeah, there's probably like a generic way to write it in terms of sort of like bottleneck type things of like mutual information before and after of the transfer function. But yeah, minimizing it is usually too hard. So people end up finding some surrogate proxy they minimize.
All right, let's thank Tarun. So we have a coffee break, so please come back here at 11:45. We'll have the mechanism section, and Mike Noiter will be up first.
Sometimes like users privacy preferences if you like time it, right? Like in that case though, like as soon as the first person's thing comes up, I pretty much get everyone else's thing. So right?
Depends. I mean, it also depends on how much information that, right? Like if I'm noise trading a very small. Yeah. Sorry. Give me a sec. How long are you here?
All of you.
Oh. Sorry. Apparently.
What you're saying and how much you.
Yeah. Fair. That's a very good point.
Good to meet you.
Good to meet you.
We did work
Been a
many
while.
years ago.
Yeah. What brings you to New York?
He was Senka.
Okay. Cool. Are you working on Babylon also?
Yeah, Babylon or Senka.
Well, he used to work at Third Chain.
Yeah. He did all about arbitrage and operating stuff. Thanks for working on a project something on.
So next time you get my new tech tweet.
I just missed like a whole
set of letters. Yeah, she was like, oh, yeah.
It's gonna be hard to
Your organization has been. It's insane.
All right.
I just want to be
We're just used to
You guys are pushing for block size.
I mean, you should submit to big conference, but then if that fails, then I would tell you when I run it again.
So I think I have a good shot.
I mean, it's what the program.
But the interesting thing is that.
I saw it was really. This is such good motivation.
Theo and I were like,
It's Osaka. It's like Osaka is the southernmost tip. And so it's like beautiful, like cultural center.
it's like the farthest island in the archipelago.
Yeah, no, it's down. It's also like it's remote, and it's like tropical. As he always does.
I know, that is their calling letters, like we're hard to get
But like, so like, rather than just sticking to it, we're actually gonna let you.
Because Bangkok. Yeah. I mean, yeah. Big stage.
I'm sure that they won't be on that. I want one of the smallest stations.
Somebody take a picture of this and send it to me because it's like they got it at 24, which basically means it's not everything. Yeah. Like 21. Well, that was for no time.
Yeah, exactly.
Yeah, exactly. 24 is only for business.
So like, and then.
David,
Oh, there you are. I was texting you out. No, I'm speaking now. I'm in this room. Oh, that's why I'm here. I'm in this room. Wait, you're in this room? 131. There was something with the name. Yeah, there's so many name tags. That I know. Something's all up here. Some of your friends who are not here. Yeah. Been forever. Right now. Yeah, dude, I was awesome. Yeah. It's actually fun. Like, what? Like the community no, like I came back here and I was like, oh, it's so dry. I have to, it's like, where I just look around and I'm like, everything's so broken.
Did you get on the subway and just feel like pure disappointment?
Well, I took a photo. So I was just like, the Japanese market not complicated. This level of fidelity. This is just. Oh, no,
Alright, that's pretty awesome.
I think you get culture shock from any other city. Yeah, like this is what we know. It's like, you know, it's like you want.
I mean, most of the islands it's like that too.
Yeah. We have like 20 more minutes, right? Before we start.
I think it's here.
Self-setup. Thanks. Hello, hello. Okay, that's too quiet, I think. Hello, 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 hello. Maybe I'll just hold it.
Excuse me. People in the chat asked if we could change the camera position.
Oh, wow. A lot of people here now. I don't know if this is loud. Hello, hello, hello. I'll just hold it, I think. Let's try some. There you go. Let's try that. Hello? Hello, hello. David, can you hear this? Through. It's pretty faint. I think I'm just gonna hold it. Why?
Can you change that?
Okay. Yeah, that sounds good. I'll just talk loud.
It was down. And sorry, like just wait 1 minute.
Let's go.
Left hand. Good live stream. All right. Sorry, y'all. We're just.
Okay. Yeah, that sounds good.
We're just adjusting the live stream 1 moment.
Having issues with it.
Yeah. Are you good? Looks promising.
And then if you could pan it up a little bit. I think that's good. Probably.
Yeah.
Thank you. So apparently the issue was that the actual slide share was lagging, and so some people were trying to watch the slides on the screens and asked that it be adjusted. Okay, so thanks everyone for coming back. So next up we have Mike Neuter, who's a researcher at the Ethereum Foundation, who's kicking off our mechanisms for MEV session.
Cool. Yeah. Thanks, Sarah, for the invitation. Hey, everyone. Hope you're doing well. Hope you're long yen. I actually was in Japan yesterday, so bear with me. I'm on a weird time zone here, but hopefully this will be fun. Yeah, the name of my talk is More Slides About Proposer-Builder Separation. This is kind of a riff on the title of an article Barnaby wrote called More Words About Proposer-Builder Separation. So yeah, it's a bit of a survey
talk. I'm not going to introduce any new concepts. It's just stuff that we've kind of been talking about and writing about, trying to fit it all into kind of a few different frameworks to understand how these pieces fit together, which is why there's a bowl of alphabet soup. I'll try and cover most things without too much detail, so hopefully everyone can follow along. Right, so before jumping in, I just wanted to shout out kind of some of the many people involved in this line of research. It truly does take a village, and I think this topic specifically has seen a ton of engagement kind of in the ecosystem broadly, which has been great. So first, hat tip to Barnaby for being a great KOL. This is an acronym I learned from Tina, which is a key opinion leader. I think that's right. And yeah, Barnaby has kind of been leading the charge, the direction of the research, and has been doing a great job summarizing things. Julian, Tomas, Francesco, and everyone has been working on a bunch of inclusion list proposals. There's like, if you're following ETH research, there's like a new proposal every week, which has been kind of maybe too much, but it's been great to see that evolve. Terrence and Potas, Terrence is in the crowd here, somewhere, who've been pushing like relentlessly on the EPBS front. It's been awesome to see. Elijah, Max, and Malesh is in the crowd too, have been talking about multiple proposers for like a year now. So it's awesome that it's getting some more airtime now. But yeah, they've kind of been leading the charge. So definitely check out some of these references and many more if you want to kind of dig deeper on these topics. But again, I'm going to kind of survey the landscape, and I thought it would make sense to start with kind of asking what we actually want from what we actually want from a PBS, mechanism. So all of these proposals are basically different ways of the protocol internalizing some view of MEV and how MEV is being extracted. So that's fundamentally what we're trying to do. And one of the kind of primary reasons for this is we want to reduce validator rewards from MEV. And this isn't like a qualitative or even a quantitative judgment on validators being like overpaid or anything, but it's more about reducing the sophistication needed to be a validator. So we want the economics of being a solo staker to kind of mirror or at least closely approximate what it would be if you're like a more sophisticated entity, a well-capitalized staking provider like Coinbase, for example. The second thing that feels like a core thing to preserve is neutrality. And the kind of one way of doing that is by hardening the protocol's censorship resistance. So neutrality is this idea that a transaction that pays the base fee and has a non-zero tip gets included in the chain. That's like an important thing to preserve, and kind of one of the core principles that these MEV enshrinement mechanisms aim to achieve. And this kind of is the time in my talk where I use this quote, which is a quote I kind of bring up every time. And it's from a Vitalik post in 2021. It says, block production is centralized, block validation is trustless and highly decentralized, and censorship is still prevented. So yeah, this is kind of from the beginning, the first half of this sentence is talking about reducing sophistication, making sure that solo staking is still a viable form of participating in the network, and you have decentralization. The decentralization is like a means to the end being censorship resistance and credible neutrality of the protocol. So I still view like these two things as very core when we're considering these MEV proposals, and I'll kind of focus deep on each of them moving forward through the rest of the talk. Now, there's a few other things that often get brought up. The first is removing relays. Relays are these trusted third parties that currently broker the exchange between a proposer and a builder. People talk a lot about how these are kind of single points of failure. There's trust. And so kind of in the spirit of minimizing trust and reducing our reliance on these actors, removing the relays is like definitely a desirable thing. I'm not sure I'm convinced that any of the proposals will actually do so, but this is something that gets brought up a lot. And lastly, I put maximally burn ETH in question mark. As you'll see, a lot of these proposals kind of end up in a situation where you have some oracle of the amount of MEV being produced during a block. Typically, the most kind of neutral way of dealing with that MEV is to burn it, because there's no real reason it should go anywhere except kind of get destroyed. So this isn't burning for the sake of burning, it's more burning for the sake of like endogenizing that value and capturing it. And this is kind of useful to think about in terms of efficiency. Like the protocol should be efficient and aware of the MEV it produces in order to like have visibility into what goes into the sequencing of the transactions. And you can also think about efficiency as like economic efficiency of transactions, like the highest paying transactions should get included. People who have, like, you shouldn't have many transactions that end up reverting on chain, these types of things. So all of this kind of comes into view when we think about how to design a PBS system for the protocol. Cool. So with all this in mind, I'm just going to run through a list of 6 different proposals. Don't worry too much about the details if you haven't seen these or read them. There's like posts about each of them. I'll highlight kind of one thing about each as we go through, and then the rest of the presentation will be trying to like put these into context with each other. So I put ePBS, oldie but goodie. So ePBS has been discussed since before the merge. Vitalik has a post from called, I forget the exact name of it, but yeah, it's pre-merge. And the whole point was to kind of separate these roles of consensus and execution. So in this picture here, the kind of one thing I'll point out, does this have a laser pointer? I don't think so. Oh, no, okay, whatever. The one thing I'll point out is on the, I think I can use my mouse. Yeah, nice. So the CL block is the consensus layer block. This is kind of the portion that the validator is responsible for producing. The execution payload is that actual set of transactions. So this is like the state update that the builders build, and it takes a lot of sophistication to sequence that part. So ePBS is just this idea of splitting these blocks into two separate things, having attestations over both of them as part of the core protocol itself. Execution tickets, this is kind of a very similar idea, but instead of the beacon block and the execution block being kind of produced by the same, well, being kind of one object from the view of the protocol, here you have kind of 2 different proposers. You have the beacon proposer and the execution proposer. That's kind of the core difference. The selection of the execution proposer happens through this mechanism of like a ticket, where a ticket is randomly selected as a lottery. So that's kind of the main idea there. Execution auctions, and again, don't worry too much about following each of these diagrams super precisely, but execution auctions is kind of similar. The protocol gives this proposing right to the beacon proposer still, but now the proposer is forced to auction it off in advance. And the difference here between tickets and execution auctions is who executes the auction itself. So in tickets, the protocol is doing the auction. In this execution auctions thing, the beacon proposer is doing the auction. That's kind of the only difference. And again, we'll highlight that moving forward. Concurrent proposers, which has kind of been the meta on Twitter for the past few days, is this idea of having multiple people produce blocks each slot instead of a single proposer. So there's kind of many different things that come into discussions around this. Mainly, if you have 2 people producing blocks, how do you get a final order on the sets of transactions that they each have? You could do deterministic ordering. You could have like a system where the transactions that they produce turn into a final set, and then you reorder those kind of arbitrarily. But yeah, that's one of the things we'll talk about. No free lunch ILs. This diagram has way too much going on, but the key point is that inclusion lists are this idea of one proposer being able to enforce some constraint on the next proposer. So even if they're not building the block themselves, they specify a set of constraints for the slot n+1 proposer. That's kind of the basic inclusion list design. The more complicated inclusion list design just has a committee of inclusion list builders. Again, this is a diagram with a lot going on, but the focus here is this tan diamond on the left, which shows that there's a committee of inclusion list proposers. You aggregate all of the committee's views together to make the final inclusion list, and that sets the constraint for the contents of the next block. Right, so that was kind of the alphabet soup portion. And now hopefully we can see how these things fit together. But before we get there, this is a very important question, which is, do you know what Jigglypuff looks like? Hopefully you do. If you don't, this is what she looks like. This will make sense in a second. Cool. Okay, back to the MEV stuff. Right. So we have our 2 things that we're trying to do. Right. We're trying to reduce sophistication and we're trying to preserve neutrality. So now I kind of think of this as a 2D space that we're fitting our 6 different designs into somewhere, and how they kind of relate to these 2 things. And I view ePBS and concurrent proposers as kind of right in the middle. Right. They're both mechanisms to reduce the sophistication required to be a validator in the system. They kind of encourage you to outsource your block production in some way, or to kind of make the block production simpler if everyone's producing blocks at the same time. And they both try and preserve the neutrality of the protocol. Now, execution auctions and execution tickets, I would say, are kind of on the left side of this space. They're more about reducing sophistication. They're trying to say, hey, there's rewards from MEV. These rewards are very difficult to extract. So we're going to make that extraction process explicit in the protocol. And everything else, they kind of ignore. And then inclusionless and fossil, the kind of two inclusionless proposals, are more on the right side of this figure. So they're more about preserving the neutrality. They're not necessarily reducing the complexity, because now you might have multiple inclusionlists that have to get aggregated together, these types of things. So it's not totally clear in terms of complexity what they do, but the goal is very explicitly to preserve the neutrality of the protocol and increase the probability that transactions are not able to be censored. Cool, so now we can start trying to connect some of these dots, right? So ePBS, to go from kind of original ePBS as we described to execution auctions, you sell slots instead of selling blocks. So what this means is in ePBS, you have to sell, when you sell a block, you also sell like specifically the contents, like the person who buys the slot has to commit to a specific block. And this means that you can only really do the auction during the slot itself, because the person competing in that auction needs to know the contents of the block while they're bidding. In execution auctions, they sell the slot outright. And this allows you to do stuff like sell it ahead of time. This might be desirable. There's kind of different views on the impact there, but that's kind of how you would transition from ePBS to execution auctions. To go from execution auctions to execution tickets, you change who actually facilitates the auction. Who's the auctioneer in this game? In execution auctions, the auctioneer is the proposer themselves. In execution tickets, the auctioneer is more like the protocol. And so that's kind of how you move from between those two data points in the space. Now, going the other direction, ePBS kind of depends on inclusion lists for credible neutrality. And to go from inclusion list to fossil, you kind of just take the number of inclusion lists and multiply it by a bunch of proposers. So that's kind of the relationship between the two. And if you actually think about fossil, which is this idea where a bunch of people produce inclusion lists, that sounds a lot like concurrent proposers. The difference between the two is that concurrent proposers might have stronger constraints on the final ordering of transactions rather than fossil. So inclusion lists just say a transaction has to be included, whereas a more strict ordering rule would say the transaction is included and this is the order in which it's executed. So that's kind of the difference between the two. Right. So hopefully you see where I'm going with this. This is why I asked you if you knew what Jigglypuff looked like. But yeah, anyway, I just came from Japan. Maybe this is like too many video game characters or something. Right. So yeah, now I think it's kind of worth taking a step back and saying, okay, we saw kind of how these two things fit together, this preserving neutrality and this reducing sophistication. Now, what are some themes that come up in the designs of these systems? So one is block co-creation. So I'll just read this sentence. Fossil, top of block, rest of block split, and concurrent proposers allow multiple parties to collaborate on block construction. So this idea is just you get a bunch of voices in the room instead of having a single leader. This reduces the monopolist power of the proposer and hopefully like leads to better censorship resistance properties, maybe leads to more competition, et cetera. Another really common theme is committee enforcement. So I'll read this sentence. Timeliness committee asserts over builder payloads. Attesters enforce bid thresholds. Validators assure availability and validity of IL objects on gossip. So this is the idea that like our security model for this whole system is an honest majority, right? And using that honest majority to curtail the power of a single party in the system is like a very common theme that comes up in all of these designs. And lastly, we have protocol incentives. So missed slot penalties to punish timing games, burning as a neutral way of internalizing MEV, and conditional tips to disincentivize censorship. I don't have time to talk about conditional tips too much, but ask Malesh or Max if you're interested. But yeah, this is kind of like the third tool in our toolkit that's very much part of these designs. So that's kind of what we're working with, but there's also some fundamental trade-offs that feel kind of inherent to the design space, and we can't really have both sides of them. So for example, auction timing. So JIT means just in time, and this is kind of the regime that we live in today. There's a block auction that takes place during the slot itself. So it happens every 12 seconds, and this is great for competition because now the builders compete every slot, and they have to be able to win the auction in order to be the producer of the block. But it has this value in flight problem, and that is, these blocks change value dramatically over the course of a slot, and in particular, right at the end of the slot, where like a lot of the arbitrage happens, the value might change dramatically, and this makes it very prone to sophistication and like latency and kind of this vertical integration that we're seeing today. Ex ante, which would be selling the slots ahead of time, like if you just did the auction like 10 minutes before the slot actually happened, you might have lower sophistication, meaning like the value doesn't change underneath you, you don't have to be co-located with the builders, but this predictability could expose sort of a different threat model, which is if a builder knows that they have multiple slots in a row, they can do multi-slot MEV. The simplest version of this is you just censor some set of transactions for the first block and include them in the second block, like once more time has elapsed. So that's kind of like one thing that it feels like when you design this auction, you have to decide where in time it's happening, and this is one of the trade-offs that I don't think you can have both of. Another example of this is, a fundamental trade-off is these transaction inclusion rules. So you could think of like a inclusion list rule that says if you have n inclusion lists, a transaction that lands in any of them is guaranteed to become part of the chain. And this has like stronger censorship resistance properties because it means, I just need one person building an inclusion list to want my transaction in, and that's like good enough. But this is potentially more gameable because then let's say there's like a deterministic ordering of transactions once they land in the list. You only have to land in one, so you might want to like bribe someone to let your transaction in late. You might play timing games around when you release the block, etc. A different transaction inclusion rule, given the same version that we had, if you have n inclusion lists and you need like maybe a quorum, like 51% or 2/3 of them to include your transaction, this might have weaker inclusion guarantees, but also has like less game ability. There's less MEV exposed by this type of thing. So kind of how the transactions actually end up getting included feels like an important trade-off that needs to be made. And then just partial synchrony. If you have faster synchrony assumptions, then things are more efficient. But if you take more time, then you have better liveness guarantees. The issues here is kind of like, okay, if you reduce slot times kind of way down to 2 seconds, then this could impact your liveness. For example, if someone isn't able to download the block in time, they can't decide which is the true head of the chain, and they end up voting incorrectly. So that's kind of another fundamental trade-off that is made when thinking about these designs. Cool. So the last minute, I'll just talk about 3 kind of different routes that we could take moving forward. The first is, and these have been discussed broadly before, but I think it's worth doing so in the context of the talk. And so the first is kind of incrementalism. So yeah, the kind of simple approach would be the one we're on now, which is you start with block auction EPBS, which is kind of MEV boost of today, and you add inclusion lists, you enshrine that. Then you go to slot auction EPBS, and then you go to execution auction. So like there's kind of a clear incremental set of steps you could take to get towards the end game if you want execution auctions as the final version of the protocol. So Max and Paradigm have been really kind of vocal on Twitter in the past few days, pushing for this kind of version of the world where you have concurrent proposers, deterministic ordering, and missed slot penalties. So this is kind of one way I could see us progressing to that. Another option is what I call Meckenstein, or Frankenism, which, yeah, fun play on words. And this idea is like, okay, let's take Fossil, which is our committee-based inclusion list design. Let's do just-in-time top-of-block auctions, and then ex-ante rest-of-block auctions. So it's pretty clear why this is like a Frankenstein of a bunch of different things. But it might solve the like value in flight problem along with kind of the multi-slot MEV things that we were talking about before. So I'm super excited about this. Like, if you want to talk about it after, super happy to think on it. Yeah, and I'll just conclude with a set of questions that are important to ask. So who's involved in block construction? When does it take place? How are the transactions sequenced? And I think number 4 is something that people don't ask enough, which is this complexity worth the enshrinement, right? So all of these things impact the fork choice rule. Fork choice is just how you decide what the head of the chain is. And all of these objects, take votes. They take some amount of network latency to propagate these messages. And all of the complexity might be worth avoiding if we can at all costs. And question 5 is the most important. Are you having fun? So thank you very much. I refer you to this block construction session document that Barnaby wrote. Again, a ton of this was coming out of these discussions. So yeah, thanks very much.
All right, any questions?
Hey, thanks for the talk. How does the concurrent proposers design tie with reducing the sophistication of the validators? I mean, is it going to be like implemented through ePBS or any kind of a PBS implementation again?
Yeah, so I think there's a few ways. I think the way Max would respond to this question is by saying there's less sophistication needed because there's less value to be extracted from being a block producer, right? If everyone's producing a block, then you don't really have that much say over the end game ordering of the transactions. So you should just produce the block based on your local view of the mempool and call it a day. There's this new proposal called Braid that he published like 2 days ago. I haven't even read it yet. So maybe things have changed since then. Maybe Milesh will talk about it. But yeah, I would say that's kind of my initial reaction.
Great. Any additional questions?
Why were the MCP emojis cows?
So whenever I refer to a staker, I use a cow because steak.
Ah, nice. But there's a steak emoji. Is
Yeah.
that just more gruesome?
Both work.
That's all I have.
The important questions.
Any other questions? All right, let's thank Mike.
Set up.
This worked a few minutes ago. Hope it'll work again. What do I need to press them?
Yeah.
Seems to go full screen.
I'm sorry, the live stream is displaying incorrectly. The tech guy is on the way over to help
Okay.
us. So
Okay.
if you don't mind just waiting
Oh,
2
yeah,
minutes.
sure. Full screen. I'm going to do this. Good. I guess.
Yeah, so the screen share is not translating to the live stream. And when we started, it was working, and then it stopped. So the live stream display. Is currently displaying that.
I guess while we wait, since there are questions about Braid, we don't have a full doc for public consumption just yet, but we're interested in some of the thoughts that led to that. There is an archive paper called Censorship Resistance in On-Chain Auctions, and there's a YouTube video of a talk that Max gave 10 days ago at Paradigm Research Day. That's been retweeted a bunch on Twitter, and you can get some of the details from there for what it's worth.
Okay, so our next speaker is Malesh Pai. Malesh is a faculty member at Rice University and is also a mechanism designer at Special Mechanism Group, which is part of Consensus.
All right. Can folks hear me just fine? Yeah? Okay. Thanks to the organizers for this wonderful day and for including this paper on the program. I didn't know Mike was going before me, or I didn't know the content of his talk, so he has previewed some of the setting the ground introduction. I'll go faster through that, but slow me down. So the point of this paper is we want to look into a tester-proposer separation, which has been proposed. It's like a catch-all moniker for execution tickets and execution auctions. And we want to point out to a centralization vector that we don't think has been pointed out yet, and we think is pretty damaging to this direction. So the outline of what I wanted to do was give you a quick refresher of proposer-builder separation. You don't necessarily need that if you were paying attention in Mike's talk, but might be useful just to strip out the part that I want to talk about. I'll talk about what is a tester-proposer separation for those of you who don't obsessively follow E3 search and the EF posts. And then this is a one-theorem paper, so it's pretty simple. All right, so why proposer-builder separation? We're at MEV Day. We kind of know the story, but the idea is that the fact that there is a leader proposing what the block, deciding what gets included, what gets excluded, what order things execute in, that makes it particularly valuable. We know it can be really valuable. So for example, Monday, while Mike was flying back from Japan after causing trouble there, blocks were selling, a single block was selling for like 360 ETH. All right, so that's over $1 million at previous prices. Exercising this monopoly right, while you have that monopoly right as a proposer, executing this monopoly right is a very specialized activity. You need access to capital to do various kinds of ARBs. You need access to searchers to do other kinds of ARBs. You need access to order flow to be able to create valuable blocks. And all of this is sort of something that the average validator proposer might not have. And there was a concern going back to well before I was involved in this space that this better access would lead to centralization. So we pulled the ripcord and we said, let's do PBS. Any proposer can show up and just say, okay, I want to sell the right. I'm going to sell my right of proposal. And these third parties that we created overnight called builders who are specializing in extracting this MEV will bid for that right. And the story was, well, if all proposers have access to this market, it's a nice level playing field and happy days are back, right? Mike alluded to this in his talk. Terence is here. He can tell you the sort of business of doing this doing this real-time selling in protocol is kind of tricky. There's a lot of work needed to make that happen. So we've not finished that work yet. So the current compromise was to do it out of protocol, right? MEV Boost, thank you Flashbots, goes ahead and does this. And to a first approximation, all I want to talk about is that it is a just-in-time auction, which means the right to propose the block is being sold in real time, all the way right up to the second you're supposed to propose the block, or in many cases, 2 seconds after you're supposed to propose the block. And secondly, it's permissionless. To a first order, anyone can become a builder and build and bid, okay? So the system is, to the purposes for what we designed it, it's working pretty well, so why change it? And there are two stories. One is we just don't like reliance on out-of-protocol sidecars. This is a critical part of the protocol's functionality, what is getting in, and we've just outsourced it to 3 builders, now 2 builders, and so on and so forth. And the second part is that the revenue from the auction accrues to the proposer, not to the protocol, not to dApps, not to users. So maybe when you sell it out of protocol, you don't know how much it's going for directly, so you can't appropriately redistribute it. So maybe we can do something different. What is a tester-proposer separation? A tester-proposer separation is the idea that being a validator currently gives you 2 rights. You get to attest to blocks. Everyone does that. And every now and then you get your lottery number called up and you get to propose a block, okay? APS just splits it and says you still have to do the consensus part, so you still get to be an attester, but the proposer right doesn't come to you automatically just because you are a validator. Instead, there is a separate right to propose the block that is being sold off. All right. We still don't know how to sell these things in real time. If we did, that would be EPBS. So what are the two proposed implementations? One proposed implementation is called execution tickets. So execution tickets is we're going to sell these lottery tickets separately from being a proposer, and in advance of the slot, the lottery winner is going to be determined, and the owner of the winning lottery ticket gets to propose that block. And the execution auction idea is some amount of time in advance. So for example, 1 epoch in advance or 2 epochs in advance, or you pick that parameter. You just auction off the right. So you get, please participate in an auction now if you want to bid, if you want to be the proposer, or if you want to own the right to be a proposer 32 blocks from now. Okay, so that's an execution auction. Now the analysis is sort of, there were these lovely ETH research posts that sort of analyzed it, and the main point that they make is that in advance of the block, no one knows what the revenue from the MEV is going to be. You don't know what the order flows are. You don't know what price movements are happening. You're 32 blocks or 64 blocks in advance. So for you, even for a sophisticated party, it's just a random number. So their sort of conjecture, if you will, was that the auction price will rise to the expectation of that random variable if you're selling it by auction, or if you're selling n tickets, it'll rise to 1 over n of that expectation. And of course, they correctly caveat that there is potential risk aversion, there are capital constraints, there's time discounting, but maybe this is okay to a first order. Okay. What is our more detailed analysis? Our more detailed analysis is roughly just because how much MEV is in the block is unknown ex ante, doesn't mean that everyone values it at expectation of that unknown value. Why? Because at the end of the day, it's an oligopolistic market. There's only 3 builders. At the time of writing these slides, it was only 3 builders, which was a month ago. If you check again today, it's like 2 builders producing 92% of our blocks. And even these builders are heterogeneous. They are heterogeneous in their ability to extract MEV. If they were homogeneous in their ability to extract MEV, you'd expect them to be winning roughly 1/3 of the time each. Thirdly, even if you win the right to be a proposer in the execution auction, nothing's stopping you from reselling that right via your own version of MEV Boost as a just-in-time thing. So we claim that this combination of things, the heterogeneity coupled with the right of resale, is going to actually change who values it at how much. So this is, by the way, the current last 14 days, as always, the lovely mevboost.pix. This is 90% of blocks are being produced by 2 builders. Why does this matter? Well, only 3 builders win 90% of the blocks. These numbers are slightly off because, but one simple thought experiment you could do is the following, which is, look, currently rsync is winning half the blocks, Titan is winning 40% of the blocks, and rsync is winning 10% of the blocks, Beaver is winning 50% of the blocks, and Titan is winning 40% of the blocks. If there was no ability to resell, then just sort of doing a back of the envelope analysis, that means that on average, because Beaver is winning the blocks most of the time, you could maybe say that Beaver has a higher expected value than Titan, has a higher expected value than rsync. So if there was no resale allowed, then you're already toast. Because you're selling the block in advance, and in advance, Beaver expects to have the highest expected value, they'll bid the most and win. Next, you'll say, aha, rights can be resold. Indeed, the proposals point out that you want an efficient market. Well, the point is that this isn't an efficient market. There are only 3 builders. So the oligopoly is something that you want to model. So let's do a simplified model. I'm going to start with, in the paper, which will be up shortly, there's a model with 3 builders, but just for the purposes of our math, let's do 2 builders today. 2 builders, that should, that should be Beaver, not rsync, I'm sorry, are winning 90% of the blocks. So there's only 2 builders for our model. And each of these builders will, in the future, at the time of proposal, have a value for the block. Builder I is going to have a value VI that's drawn from some distribution. Each party understands the other party's distribution. We're going to assume that these 2 distributions are independent. And the critical assumption we're going to make is that builder 1's distribution of values, the distribution of the value that they will have in the future, is dominant over the other ones in the hazard rate order. So the hazard rate order is a particular order that among stochastic orders, it implies first order stochastic dominance. So you can think of it as saying it is a slightly stronger version of just saying that on average, builder 1 expects to have a higher value than builder 2. Okay? So this is our simple game tree, which is you do the execution auction in period 1. Once the execution auction happens, either builder 1 wins or builder 2 wins. Let's not worry about the case where some third anon wins it and then tries to resell it to builder 1 or builder 2. In period 2, nature is actually, the actual block is going to come around, and these builders are going to actually get the values that they have for the right to propose that particular block, but they can potentially turn around and resell. So even though I, as Beaver, have a value of 1 ETH for the block, I can go ahead to Titan and say, hey, Titan, would you like to buy this block out from me? Now, what's important to notice here is that if I'm only selling to one builder, I don't necessarily want to, if I have a 1 ETH value block, the optimal thing for me to do is not to offer it to the other guy at 1 ETH. Then I get 1 ETH either way, whether he buys it from me or whether he doesn't buy it from me and I propose my 1 ETH block. What I should do is offer a higher price, which sort of optimally maximizes my expected revenue, and expected revenue being whatever price I offer to him times the probability he buys, plus the probability that he doesn't buy times my 1 ETH. So each builder is going to offer a value, offer the proposal right up for resale with a reserve price that depends on their own value. The theorem is just straightforward. If we have 2 builders, and this extends, if we have 2 builders and one builder is better than the other in the hazard rate order, then in the equilibrium, builder 1 always wins the period 1 execution auction. It's not just that builder 1 always wins the period 1 execution auction. In equilibrium, builder 1, because they're marking up the price when they resell it, ends up proposing the blocks more often than they would have if the blocks were sold in real time. So we think this is a massive centralization vector. How am I doing on time? Sorry. Yeah. So the proof idea is fairly straightforward. You just solve the game tree by backward induction. So in let's just imagine that builder 1 wins the auction. So if builder 1 wins the auction in period 2, they have the right to propose. They also have the right to resell this block to builder 2. They know their own value for the block. Let's call that V1. Well, what is the optimal offer for them to make to builder 2? Well, it's the optimal offer is the value V that solves this one equation on the board. Okay, so this is their value that maximizes their expected revenue. If builder 2 says, nah, that's too rich for me, I'm not going to take you up on that, then I just turn around and propose the block that I have and take home V1. Okay, so that's what I'm going to do in V1. Now, that's what I'm going to do in period 2. Each builder understands that they're going to do this in period 2, that they're going to resell the block, or they're going to try to resell the block with a markup relative to their own price. So now you can do the backward induction and ask, in period 1, how should I bid? Well, I understand that in period 1, if I own the resale right, then I get to run this optimal auction. If I don't own the resale right, then I am stuck sort of with just whatever surplus I make when the other guy tries to resell it to me. So you can calculate those 2 numbers. The first one is my expected revenue from the optimal auction. The second one is my expected revenue from buying it off, expected net profit from buying it off the other guy. my willingness to pay in period 1 is the difference between these two numbers. And the main part of the proof is just to show that under our assumptions, builder 1 is always willing to pay more than builder 2 for the execution auction. We then, you might say, okay, this optimal auction sounds kind of funky, and you only have 2 builders. So we just went ahead and did this with 3 builders. So we redid it numerically with 3 builders, and we did something simple. Like we said, when the builder wins whichever builder wins in the first round, goes ahead and offers it up for a 10% markup. So they know their own value. In the second round, they're just going to sell it to whoever comes at a 10% markup. That's better for them in terms of expected revenue than selling it at their own value. Well, what happens if you do that? Well, these are not to scale, but this gives you the same sort of idea. The same things happen, which is if you were doing it as a JIT, if you were selling it using the current MEV boost, then you get whatever current market shares there are, and you get the distribution of surpluses, profits across the builders that you currently see. If instead you sell it as a execution auction, then the pink guy, the guy who was winning most often in the first round, in the old world, in the MEV boost world, will now win the execution auction every time. They will then propose the actual block more often than they would have under MEV boost. And they're going to have a lion's share of the actual realized surplus relative to what the other people make. Okay, so that's our main sort of punchline. What are the takeaways? The takeaways are, well, JIT auctions are hard, maybe impossible. I don't know. Smarter people than me on these things are working on that. But the important thing about JIT auctions is that they allow realized values to matter. And this means that even if you're a statistically weaker builder, sometimes you just happen to have some really juicy order flow, and you can win out a few blocks. But in the absence of your realized value being able to matter, in the ahead of time auction, the statistically stronger builder is always going to win the auction, and they're going to be able to squeeze these other builders out. This could have, in the long term, this could be even worse for us because, who'd want to be the 7th largest builder in this environment? So, and of course, as Mike already pointed out, this centralization or monopolization vector could further, the fact that this is happening means that the fact that there's one guy under our model who's winning every execution auction means that they don't have to resell. They could even do more harmful stuff like multi-block MEV, which can be extremely destabilizing for DeFi. But this model is not driven by the fact that you have attacks like multi-block MEV enabled by execution auction. We've not formally modeled execution tickets in this setting because execution tickets, you'd have to tell me exactly how these execution tickets are being sold. That's underspecified right now. But the main point is the same idea goes through in the execution tickets in the sense that when you think about who values execution tickets, any given execution tickets, builder 1 is going to value execution tickets more than everyone else. Okay? So that's the paper. That's my talk. All right. Elaine had a question. Alex had a question.
Questions?
Oh.
Yeah.
Elaine's hand went up first. I'll go with that. Sorry?
Can you go back to that game tree? I guess I don't understand the game, or maybe I'm lost on the notation. So V1 and V2 are fixed, or they're random variables?
They're random, but they're only realized in period 2.
So V1 and V2 are random variables?
Yes. They're random variables that are drawn from known distributions. So this is a game of incomplete information. In period 1, I know that I will have a value drawn from this distribution. In period 2, I actually get that value from that distribution.
So basically V1 is like when the block and when the transactions actually come,
yes.
how much the
MEV is in that. Yeah.
I see. Okay, I see.
So one of the interesting things about private order flow is that it accumulates, and what that results in is a block value that is in some way actually dependent on how long since the last block that proposer or that builder was included. You go 10 blocks in a row without a block, you have a lot of private order flow. That's very valuable. How would something like that impact this model?
You're right about that, but now think, I guess, if you take the current private order flow contracts as fixed, then you're right that, 8 blocks in, I haven't won any execution auctions. I have a ton of private order flow for 32 blocks from now. I know that I want to win because I will have something like that. But if you think one step back, how much do I sign? Who do I sign with? Already, it's tricky for me to sign as a private order flow provider with anyone other than SAP or Titan, but now it's going to be even worse, right? There's one guy who's winning all the execution auctions. So it's but you're right. If a big private order flow provider went to somebody who was a suboptimal builder, they could stay relevant for much longer.
Got it. That makes sense.
That's outside the model. Yeah.
Thank you.
Quintus has had his hand up. Or I don't know. Yeah, you can always catch me later. Whoever. And then there was one more, sorry.
Yeah.
Sorry, Marcus. I guess just a comment on the order flow thing. I think there's actually a lot of open questions that come out of that, because right now there's this incentive for builders to treat their flow well, because they have this repeated gain, they want the flow to come back. But in a world where you are the monopolist, there's no real incentive to do that, and so that probably changes the how order flow gets executed. Probably there's much more incentive for builders to sandwich, etc. But my question was, so in this second period, I wasn't sure what kind of auction you were discussing, and I was curious. I would imagine probably you have the same result, but I'd wonder if you've thought about a setting where you have some sort of we require the holder of an execution right to post a price in some sort of a Harburger tax kind of setup. Do you think that changes things?
Depends on when they have to post that price. If they have to post that price just in time, the main point is they're never going to post that price equal to their value for the block, because that's just a strictly dominated strategy. I already have a block that's worth 1 ETH. I should never offer to sell it to you for 1 ETH, right? I can get 1 ETH just by proposing my own block. So whatever it is, 1.1, 1.2, you believe our math, but I will have an advantage because I will mark up my block I will mark up the resale relative to the right I have. And you can't stop me from doing that.
Right. I think what you would ideally want, and I don't know if this is possible, is to require them to post the price as soon as they hold the right, and then and then tax them in some way to disincentivize them from stating a very large number.
Well, but if there's no new information that's come in from the moment they own the right, they're going to put up basically their willingness to pay in the ex-ante auction, which is higher than anyone else's willingness to pay. It's only exposed when I suddenly say, oh, I'm an inferior builder to Quintus, but I got a bunch of order flow, or I got a bunch of searcher flow, or something happened, and I want to outbid you. That's when I can turn around and want to win you. But if you're the statistically strongest builder, long before we know anything, you're the only person you're willing to go to a price that no one else is willing to go.
Yeah, okay. I don't want to drag this on too much longer, but I'll just make a last point before I give back the mic. I think that I didn't understand that point really, because surely the valuations are evolving as time goes by and more information is revealed. Yeah. And if the price is posted on chain for that whole period, I relinquished the mic.
If you could do real-time updates, maybe that would change things. But really what we're talking about is 32 blocks before, and then most of the information is maybe 1 or 2 blocks in. So we'll be back to similar problems, I think.
Okay, and we'll take one more quick question while Kartik sets up, please.
Sorry.
Thanks. So just quick one. We already enforce client diversity by bullying large staking pools into running multiple clients. What if we just don't? What if, in the no resale allowed scenario? What if we just also bully large proposer pools into selling to multiple builders?
I mean, I think we enforce the sort of client diversity. Well, we don't enforce the client diversity. We sort of do it, but the Sybil problem in builders is probably large, right? Like,
yeah, it's so the sibling definitely becomes an issue, but it's kind of interesting.
Titan becomes Titan 1, Titan 2, Titan 3. So yeah, that's I think a concern.
Is that one chart? Is that one? This one is one for sure.
Let's thank Malesh. So our next speaker will be Kartik Nayak, who is a professor at Duke. Kartik.
Thank you so much. Am I audible? All right. Thank you so much for inviting me. I'm very happy to be here. And today I'll be talking about Sailfish, a latency-efficient DAG-based protocol. So this is joint work with Nibesh and Aniket. So we've been talking about multiple proposers, and DAG-based protocols are, a natural way to have multiple proposers. So the talk will be split into two parts. The first part of the talk, I'll try to compare and contrast, DAG-based protocols with leader-based protocols and try to see, what the differences between the two are. And this will be the smaller portion of my talk. And in the second part of my talk, I will talk about, this protocol itself and an analysis on this protocol. So the problem we're talking about is state machine replication, where there are a group of parties who agree on a sequence of transactions submitted by external clients. And they do this even if some of these parties are faulty. Okay, so you have transactions coming in one at a time, they agree, and they output these blocks. There are two key properties that we are looking for, safety and liveness. Safety says that two non-faulty parties do not disagree. And liveness says that a transaction proposed will be eventually executed. So we want to achieve both of these properties, safety and liveness, even when some of these parties may be Byzantine. So let's say some T out of n, up to T out of n parties are Byzantine. And you want this to hold under different network conditions. So the network condition of interest over here for us is going to be partial synchrony, where the network can be asynchronous for a while, but eventually it is synchronous. And it is customary to solve this problem for T less than n over 3 under partial synchrony. And if you look at this historically, there are two key metrics that people have tried to optimize. One is latency and one is communication complexity. So latency says that the time to commit latency is the time to commit a client transaction, and communication complexity is the amount of communication and bits that happens in between parties. And if you go back to the literature and look at all of the protocols, you would find that most, at least many of these protocols, they have an approach which follows, roughly speaking, the phase king paradigm, where there is a designated party called as the leader, and the leader is responsible for proposing blocks of transactions and getting all parties to agree on them. Okay? If the leader is malicious, of course, you cannot expect progress. But if the leader is honest and if the network is good, then you expect progress as well as safety. So many protocols such as PBFT, Tendermint, Hotstuff, Pala, and so on, follow this structure. And in fact, if you look at the latency and communication complexity metrics, PBFT already gives you from 2000 gives you ideal latency. Hotstuff 2 give you ideal communication complexity. So then a natural question is, aren't we done? Do we need anything more? Well, what about throughput? So intuitively or theoretically, we always we relate communication complexity and throughput, right? So if you have low communication complexity, it implies, you can get a high throughput. But in leader-based protocols, it turns out that your leader can be a bottleneck. Okay, and this can happen in two different ways. So first concern over here is unequal scheduling of work, where you can have a leader, let's say you have a 1,000-party system, and let's say in a vanilla leader-based protocol, it is sending a 1 megabyte block. So if it is sending to 1,000 different parties, then it is sending effectively 1 gigabyte worth of information. But if you look at this from the perspective of individual parties, they're only accepting 1 megabyte worth of information. So there is unequal resource usage in that sense. And second, if the leader fails, of course, we'll change the leader and eventually the protocol will progress. But for that time being, there is no progress that happens. So because of these reasons, despite having good communication complexity, we may not have good throughput. And these are known problems with leader-based protocols, and there have been approaches to improving throughput. So there are notions called as extension protocols, where you extend 1-bit consensus to L-bit consensus. And the key idea over here relies on erasure coding techniques to improve throughput. So there is this other line of work called data availability oracles. Danksharding, Tiramisu are examples over here. Even over there, they rely on erasure coding techniques. In fact, the first 2 lines of work, they are similar. It's just different names by different groups of people. There is a different technique called Narwhal, which is a systems level optimization that separates transaction dissemination from consensus. So you rely on different worker nodes to actually transmit data. So all of these approaches really do help in improving throughput. So this new line of work on DAG-based protocols actually, address both of these concerns in a more natural manner. And they do this by ensuring that every party performs a similar amount of work at all points of time. So because they're doing similar work at all points of time, it fundamentally solves this unequal scheduling problem that we were discussing earlier. And second, because your DAG construction itself does not rely on the leader, so you have a situation where even if a leader fails, the construction proceeds, and eventually you will see progress. So the disadvantage, though, is since everyone is working at all points of time, you do have high communication complexity. So before we move on to talking about our protocol itself, I want to make one comment on the terminology itself. So both of these terms, leader-based or DAG-based, they're actually misleading terms. If you think about it, many leader-based protocols construct chains, which are DAGs, and DAG-based protocols typically rely on leaders to achieve consensus. So in my view, the key properties that are achieved by DAG-based protocols are the 2 properties that I described earlier. And while leader-based protocols can give you these properties in some ways or some subset of these properties, DAG-based protocols give them to you in a very natural manner. With that, if you look at existing DAG-based protocols, they give you improved throughput at the expense of communication complexity for small to moderate-sized settings. But they do not achieve ideal latency. And that was the focus of our work on Sailfish. So we asked, can we obtain DAG-based protocols with ideal latency? So in the following, I'm going to describe the core structure of a protocol. And I'll tell you at a high level what the core safety argument is, and I'll show you a couple of graphs on performance. Okay, so it's a DAG-based protocol. So everyone is maintaining a DAG. So what you see to the left over here is the frontier of the DAG for a given party at the end of round R-1. Okay, so you move from round R-1 to round R. So party, let's say the first party over here, proposes a block. It points to 2t plus 1 vertices from the previous layer. And similarly, other parties will propose similar blocks. Okay, so over here, when I say, you're pointing to 2t plus 1 vertices delivered from the previous round, I mean it in a very specific sense, where this delivery happens by a reliable broadcast protocol. So you propose it, you pass it through a reliable broadcast, and once the reliable broadcast protocol ends, it delivers. That is when we call it as delivered. And this, it turns out, it gives you 2 nice properties. One is non-equivocation, and one is totality. So non-equivocation says that, if I have delivered a block from a given party in a given round, no other party will deliver a different block by the same party in the same round. And totality says that if once I have delivered a block, everyone will deliver this block eventually. So together, what this ensures, if you apply this for every vertex, what this ensures is that, eventually every party is going to build the same DAG. Okay, so if everyone is going to build the same DAG, aren't we done? Don't we have agreement? Why do we need any consensus? Well, if you look at the view of any party at any point in time, that may be different. Eventually they're going to be the same for a given round, but for now they may be different. So as an example, the view of party PI over here at round R may be that it has received the first 3 vertices, but not the last one. And for PK, it may be the case that it has received 1, 2, 4 and not vertex 3. Eventually they'll receive it, but if I have to order right now, that may not be the case. And this is why we need agreement on whether a vertex is delivered. So how do we obtain consensus and order these vertices? In our protocol, we have these designated parties called leaders. So the vertex that has a symbol, the leader symbol on it, is the leader for that vertex. And let's assume that everyone knows who the leaders are for each of these rounds. So our goal is to commit a leader vertex in any round. So if I'm committing a leader vertex in round R, what we do is all of the parties in round R plus 1, they prioritize pointing to the leader vertex in round R. So they will wait for the leader vertex until some timeout and make sure that they point to it. If it doesn't arrive by then, maybe they won't, but until then they will try to prioritize pointing to the leader vertex. Okay, and if it so happens that this leader vertex in round R, let's call it vertex V, if it receives more than 2t plus 1 votes, or there are more than 2t plus 1 vertices from round R plus 1 pointing to it, then we can commit this leader vertex. And this is when I'm going to order some vertices in the past. Okay, so you do this in 2 steps. The first step is you try to find path to a leader vertex in previous rounds, so the largest previous round, and you try to recursively commit vertices in that round. So as an example over here, this round R leader vertex is pointing to this round R minus 1 leader vertex. So you try to recursively commit this round R minus 1 leader vertex if you haven't done so. And then you order all of the vertices that remain that are still pointed to by this round R leader vertex. So you can apply any deterministic ordering that you prefer. So that's the protocol over here. There's just one step that I haven't mentioned. So you prioritize pointing to the leader vertex. What if the round R leader is Byzantine? We know that because we are using reliable broadcast, it cannot equivocate. But what it can do is, it can feign a crash. It can ensure that you do not receive this delivered block at all. Perhaps no one receives it. So if a round R leader vertex is not delivered in a given amount of time, let's say until some timeout, all of these parties send a no vote message to the next leader. And this next round leader, round R plus 1 leader, would use a certificate of 2t plus 1 parties stating that we haven't voted or we haven't delivered this round R leader. So it uses this to justify the fact that this round R leader does not exist. So if from round R plus 1 leader's perspective, either I point to the previous leader or I show this certificate saying that this leader does not exist. Yeah, so that's the protocol. And the safety argument over here is actually quite neat. So let's look at, if we want to ensure everyone has the same ordering, what do we actually need? So the core guarantee we want is the following. Let's say there is some vertex, some party that has committed a round R leader. Okay, and let's say there is some other party who has not committed this round R leader by satisfying the rule that we described earlier, because maybe some vertex was not received in time and it could not see the 2t plus 1 votes. But it commits some other vertex in a higher round R prime. Okay, what we want to ensure is that both of these parties order all of the transactions that they have received in the same order. Okay, and because when we are committing this higher round leader vertex, we are trying to find a path to a previous leader. What we want is to ensure is that this path really exists. Okay, so if some party commits a round R leader vertex, then there is a path from round R prime leader vertex to this vertex, and this should hold for any higher R prime. let us see how we can, satisfy this claim. And we'll do this in two parts. We'll first talk about when R prime is the immediate next round, and then we'll talk about any higher R prime. Okay. So when R prime is the immediate next round, observe that there are 2t plus 1 votes from around R plus 1 on around R leader vertex. And out of these 2t plus 1 votes, t plus 1 of them are coming from honest parties. And since if they vote, they will not send a no vote message to the next leader, a no vote certificate cannot exist that is sent to the next leader. And if the next leader has to exist, it has to point to this around R leader vertex, because it only has two options, either show a no vote certificate or point to the previous leader vertex. So for this reason, it has to point to the previous leader vertex. So this is part one. For an argument for higher rounds is simple, and I'll show you an argument for R plus 2 and for R plus 3 and so on. The same or a similar argument actually holds. Over here, we are interested in two different quorums. The first quorum over here is Q1. So in round R, so in round R plus 1, observe that 2t plus 1 parties are pointing to this round R leader vertex. And let's say this quorum is quorum Q1. It is denoted in orange color, right? If I look at the leader vertex in round R plus 2 now, it also has to point to 2t plus 1 vertices in round R plus 1, right? So this is denoted using the green arrows, and let's call this quorum Q2. Okay, so the two quorums Q1 and Q2 has to intersect in t plus 1 vertices. And out of these t plus 1 vertices, up to t may be Byzantine, and there has to be at least one honest vertex, because of which there will exist a path from the leader vertex in round R plus 2 to the leader vertex in round R. So that's the core safety argument for the protocol. In terms of latency, what a leader vertex of round R gets committed in round R plus 1. So essentially it's 2 RBCs, but it turns out that you don't need to wait until 2 RBCs are done to actually commit this leader vertex. In fact, because of the way our quorums are aligned, for the second in round R plus 1, you can actually commit as soon as the first message in the RBC is received, because of which the latency to commit is 1 RBC plus 1 delta. Okay, and for non-leader vertices, when you commit round R leader vertex, you commit non-leader vertices from round R minus 1 as well, and they were proposed one round earlier, so that's why it requires one additional RBC to commit them. So the key advantages of Sailfish are, it's the latency. You achieve 1 RBC plus 1 delta and 2 RBC plus 1 delta respectively, and this is better compared to all prior work. Second, the protocol has a leader in every RBC round. So this is compared to state-of-the-art protocols like Shoal. This improves on the latency of non-leader vertices. And finally, the architecture over here, by relying on RBCs, it simplifies things quite a bit compared to works like Cordial Miners and Mysticity, which open all of these black boxes. So the final thing that I want to mention is the performance results. We spoke about things happening in theory. Can we observe these latency advantages that we see in theory in practice? Okay, so we compared our results with Bullshark and Shoal, and we set up. We actually modified Bullshark's code to accommodate Sailfish, and we set up our experiments in such a way that all of them were geo-distributed in 5 GCP regions. And here's a quick graph that we have. On the x-axis, you have throughput, and on the y-axis, you see latency. There are 3 different curves over here, one for Bullshark, one for Shoal, and one for Sailfish. So the way these experiments are performed is, you keep adding more and more transactions to the system until the system, so initially the system can handle it, and that's why, your latency stays flat, even when your throughput is increasing. And at some point, the system cannot handle it, and at that point, all of the transactions are buffering, and eventually the latency shoots up. So you always see these hockey stick curves, and what we're interested in is the inflection point. Okay, so because this is a throughput versus latency curve, higher throughput and low latency is good. So to the right and lower is good. And as you can see with Sailfish, with the blue curve, you see it is to the right and lower than the other two. And in terms of how does it scale with respect to the number of parties? Over here, we conducted these experiments for different network sizes, 10, 20, and 50. And as you can see, everything that we said in terms of latency holds true as we scale n as well. So on the y-axis, you have latency, and the blue line is always lower than the orange and the red line. Okay, so with that, let me conclude my talk. So we first spoke about DAG-based protocols. We observed that the key things that they give you are equal scheduling of work and progress at all times. Then we spoke about Sailfish, which runs in RBC-based rounds, and we saw that it achieves a latency of 1 RBC plus 1 delta and 2 RBC plus 1 delta for leader and non-leader vertices respectively. And there's a third part which we actually did not discuss in the talk, that is supporting multiple leaders in a given round. Thank you, and I'd be happy to take questions.
Hi. So there is a theoretical minimum latency in which consensus can be run, at least with this failure tolerance. And if I recall, it's about the same as the theoretical minimum latency for RBC. So is there any hope for getting the latency for something like a DAG-based protocol like Sailfish down to the theoretical minimum for consensus, or is there a fundamental difference between the latency these kinds of things take?
So the theorem minimum latency for consensus or Byzantine broadcast in partial synchrony is 3 delta. And over here, 1 RBC, if you assume a latency efficient RBC, it's 2 delta time. So 2 delta plus 1 delta is 3 delta. So over here for leader vertex, we already achieved theoretical minimum latency.
Okay.
Any other questions? All right, let's thank our speaker.
Thank you.
Okay, so we'll now break for lunch. We'll be back here right at 2 to start the next session. You can get lunch from either the first floor or the basement. They'll have stations set up in both. There's a little bit of seating indoors, but recommend going outside too. All right, thank you for coming back from lunch. So we're going to get started with session 3. Our first speaker in session 3 is going to be Chris Kogel, who's a researcher at the University of Zurich.
Hello, everyone. So the mic is working. It's great to be here with you. Today I'm going to tell you a little more about a new thing, which is cross-rollup MEV. I am a researcher at Matter Labs and also a PhD candidate at University of Zurich. And generally my PhD research is about security and scalability of DeFi. And simply layer 2s and MEV is where those areas intersect with each other. I hope that today I also give you some background information why actually people are doing MEV, what you can extract and where, and highlight those new places like L2s where you can look for that. Such those layer 2s and the rollups are becoming more and more important. You can see that the whole decentralized finance was born on the Ethereum blockchain in 2018, with Uniswap being the first exchange. But you can see that over time, mostly because of the high gas fees, the trading volume is moving away from Ethereum to another blockchains. And it's not only Solana where the trading volume is moving. You can see on this chart that a very big part of the trading volume is moving away from Ethereum to those layer 2 blockchains that are based on the Ethereum. Also, the Ethereum is currently having a rollup centric roadmap, and this is being encouraged by the Ethereum itself to move the user activity to rollups. When you look at the numbers, there are actually already more swaps, more swap transactions happening at rollups such as Arbitrum or Base than on the Ethereum mainnet. It's just they are still smaller in volumes. But maybe a very brief repetition about what is arbitrage, because the more decentralized exchanges we're having, the more L2s we are having. It means there are more trading venues. And the arbitrage is simply a situation where you can buy some cryptocurrency at one exchange for a lower price and sell it at another trading venue for a higher price. And you can see here example where you can buy something at AMM, like one ETH for $2,300 and sell it at Binance for $2,400. And this is simply arbitrage because it's almost risk-free reward. And simply what we are asking ourselves in our research paper is, are there price differences between the decentralized exchanges that are located on Ethereum and on the layer 2s and also a Binance? Because in theory, if the market is efficient, the prices everywhere should be equal. This is question number 1. Question number 2 is, if there are those differences, how big they are, and can they lead to the arbitrage opportunities? So are those differences in prices big enough to cover the bridging costs, to cover the transaction costs, and other related costs? And then the third thing is actually the most interesting, is how to explore those opportunities. So how can we make sure that actually we will be the ones that are exploiting that arbitrage MEV? And now maybe how MEV is working on Ethereum. There are generally three types of MEV. It's back running, front running, or the combination of the above. And the biggest part of the MEV on Ethereum is actually back running, which is when there is a target transaction and the MEV searcher wants to put his transaction just after the target transaction. And typically, the target transaction is a transaction that is, for example, causing a big, swap on the exchange, causing a big price differences between a DEX and another DEX or SEX. And then, we simply want that our transaction will be as close as possible, ideally just after that swap transaction that caused that pricing imbalance. Another application of that MEV backgrounding is in the DeFi lending. It's about liquidation, when you want to liquidate the bad debt as soon as possible. It's also linked to the Oracle extractable value. And actually, when you look at the numbers, like over 70% of the MEV on Ethereum mainnet is related to the arbitrage. So it's simply looking for that price differences between different trading venues. And also from that arbitrage MEV, over 60% is actually related to the CeFi DeFi arbitrage. So when you are simply trying to exploit the price differences between the DEXs on Ethereum and the Binance, Kraken, and other centralized exchanges, and only 30% is actually related to the cyclic arbitrage within the same network. And then the question is it the same, or will it be the same on the rollups? So actually, just to make sure that everybody knows what the layer 2 and the rollup is. I mean, I will be using those words interchangeably, although they are not the same, but they are almost the same. Like simply a rollup and the layer 2 is a scaling solution where you take complex calculations outside of the Ethereum, use those calculations, and then you store back the results. There are different types of the rollups: optimistic, zero knowledge, and they typically have the one major component, which is called the sequencer, which is actually super important for the layer 2 blockchain, because it's the sequencer who is producing the blocks and deciding on the order of a transaction within the block. I mean, today, almost all of the rollups and all of the major rollups are running only one sequencer. That's why there's the problem of a centralized sequencer with the rollups. And generally, we are trusting those centralized sequencers because they are operated by the foundations that are simply standing behind those rollups. And what's actually important, as a consequence, we don't have those MEV auctions like Flashbot style solutions on layer 2s. I mean, typically, when you think about layer 2s, you think about two things. So first of all, is the Ethereum security and lower gas fees. But those two other components, they are also very important when you look at the decentralized finance on L2s. Because as I mentioned to you, there are no MEV auctions, boost auctions yet. And also the block production is much faster. I mean, on Ethereum, it takes between 10 to 12 seconds to produce a block, whereas on the rollup, I mean, depending on the implementation, it's around 1-2 seconds, or sometimes even 200 milliseconds. And this is significantly changing the MEV strategies on L2s. And simply, now let's look at the results that we achieved. You can see on this matrix behind me the price comparison between Uniswap V3 pools of ETH and USDC. We simply compare the prices for the first half of this year per block frequency between the deployment of Uniswap across Ethereum and its five major rollups. And you can see that actually there are some differences. There are like, I mean, one of the biggest differences are on the ZK sync, followed by the big differences with base. And then the natural question then that you can ask is, are those price differences big enough to cover the costs of extracting them? And also, once you see that there is a price difference between the Uniswap, for example, on ZK Sync and Uniswap on Arbitrum, how big the transaction should be. So actually, what you can do, you can calculate the optimal size of optimal volume of a transaction that is exploiting those price disparities. I mean, depending on the AMM type, the formula is simpler or more complex. For the Uniswap V2, it's actually quite simple. Here you can see the transaction volume, which is equaling the size of the transaction volume, which is equaling the price differences between the DEX and SEX. And here you can see actually how much money the arbitrageurs is making. And here you can see that actually it's increasing. Yeah, the bigger the transaction is, but there's always like one point when it's the optimal and it's the highest value. It's also related to the fact that typically those AMM functions are concave. And yeah, depending on the complexity of that AMM function, you can simply calculate and find those points. And this is simply what we did in our what we are doing in our research. And in the first part of that research, we actually compared the prices between the SyncSwap, which is the largest AMM fork of the Uniswap v2 on the zkSync, with the prices on Binance. You can see here above the biggest daily price difference. And here you can see in the blue actually how much the arbitrageurs was actually making each day. And I mean, it's rather intuitive that the bigger the price difference, also the higher was the revenue of the arbitrageurs. However, you can see that here is the size of the liquidity pool or the reserves inside the AMM. And it's playing important role because you can see that actually even on the days when the price differences were bigger, but the liquidity pool was lower, like in that case, arbitrageurs were making less money than here on that point, where simply the smaller price difference led to the higher revenues of the arbitrageurs. So it's very important to look, when you're trying to estimate the profit of the arbitrageurs, to look not only on the price difference, but also how big those liquidity pools are there. And in the next step, we simply make that formula more generalized for also applicable for Uniswap v3, and we simply start to compare how much you can extract in profit between different rollups. And you can see here because, for example, the pools on the Uniswap at zkSync are not too big at that point, like the profits were rather low compared to the other Uniswap deployments. And here the highest revenue of the arbitrageurs are here in this area. So between Ethereum and the different deployments on Arbitrum. And you can see that actually the cross-rollup arbitrage can be even higher between the rollups than between a Binance and another rollups. Here actually the highest arbitrage, we calculated we found between the Binance and Ethereum, but quite often between the rollups, cross-rollups is actually higher than between a rollup and a Binance, which is most of arbitrageurs are doing today. But then the next question, actually you can ask yourself, okay, once we know how big is that, we know the price difference, we know how big the profit of the arbitrageur can be, then how can we assure that we will win that profit, that nobody will front run us? I mean, on Ethereum it's possible. On Ethereum it's possible, on the rollups it's not possible. Maybe another important thing is, I forgot to mention, is that you can look here, that those price differences, they last quite long. We simply calculated how much time does it take between the prices at those Uniswap deployments and the Binance, they become equal with each other. On Ethereum, it's like 31 seconds. On Arbitrum, 7 seconds, and other chains more. But here, you also need to remember, when you look at those seconds, that there is a different block production. Because, I mean, 30 seconds on Ethereum, it's maybe 2.5 blocks. Whereas on Arbitrum, I mean, 7 seconds means almost 30 blocks. Because the block production is much faster. And this has a big impact on the extraction of that arbitrage MEV, because typically even not typically, if not always, on the L2, when you have a target transaction that is causing some big price differences and you're trying to exploit it, your transaction, your MEV transaction will be in the second block after it. So it's almost impossible unless, you apply some certain strategies to be within the same block. It's also related to the fact that the blocks are produced much faster. And then there are two options that you can apply to exploit the MEV on L2s. One is when there are DEXs within the same blockchain, like in that case. There are like two DEXs, for example, on optimism, and you can equal the price between them, or you can look for like a triangular arbitrage, like between the three different tokens and the pools, and then try to equal those prices in one atomic transaction. And the people are already doing it. You can see how much of such atomic arbitrage was already exploited. But I mean, remember that actually on Ethereum, that type of the arbitrage, atomic arbitrage between DEXs corresponds only to 30–40% of the total arbitrage. Meaning that if we are compared to the Ethereum, still 70% of MEV is not captured here. And here, when it comes to the looking for non-atomic arbitrage on the L2s, which can be between the L2 and the rollup, or between two rollups, there are three different possibilities. So one is, but I mean, most of the rollups don't support that. You can take part, you can simply pay a higher gas fees to increase the chances that your transaction will be executed faster. But what actually a lot of people are doing, they are looking for the sequencers that are running the rollups, and they are simply trying to be as close as possible to that sequencer. So this is the old school approach known from the traditional finance and high frequency trading. And another thing that you can try to do, you can simply spam the network with your transactions, because the gas fees are actually super cheap on the rollups. And I mean, all those things are actually already happening. Especially that in March this year, the Ethereum underwent a very big upgrade. It was called Dekun upgrade. Happened here on the 13th of March. It introduced the blobs, and as a result, gas fees on the rollups went down almost to 1 cent and below, which is making doing any transactions on the rollups super cheap. And because it's so cheap to do transactions on the rollups, you can simply take a risk of doing that non-atomic arbitrage transactions. Because even if your transaction is not successful, you run it too late, I mean, you will lose, I mean, it can be reverted, you need to pay a gas fee, but the gas fee is so low that you don't risk much. And you can see that actually the amount of the reverted transactions after that Dekun upgrade increased hugely after that Dekun upgrade. And then, actually, I already mentioned that when you are the arbitrager trying to execute that arbitrage MEV between two rollups, your biggest risk is that is called the price or state drift, meaning that you buy, for example, an asset on one rollup, but you don't manage to sell it on another rollup before the price changes. And there are different approaches how it can be mitigated. One of them, which is actively being researched, I think also by Flashbots, is about introducing time boost auctions inside the sequencers of rollups, where you'll be simply paying more for getting like a super speed for your transaction. I mean, as you are anyway paying maybe to a DeFi solver for getting close to the, getting physically close to the sequencer, why not, instead of doing that, simply take part in that boost auction. Another approach is actually using a so-called shared sequencing, which is under a heavy development within the L2 community. And such shared sequencer is quite important because, let's say, in the final stages of its implementation, it can allow for two things. Like one thing is can make simply the transactions across two rollups atomic. So simply that non-atomic arbitrage can become atomic arbitrage, eliminating the risk for the arbitrageurs. And also the second thing that such a shared sequencing can bring is the shared liquidity, meaning that you'll be able to reuse pools on different rollups or move your reuse on one rollup tokens from another one. This is actually something that we are actively researching at Matter Labs. Also, yeah, my colleagues are here who are really studying it. If you are interested, have a chat with us. And then, yeah, that was my talk. If you have any questions, yeah, feel free to ask. Thank you.
Yeah, Chris, good to see you again. Just wanted to ask you a question. How much of L2 arbitrage is open because your sort of traditional arbitrageurs on L1 just don't want to keep liquidity on the chain? So is it really an atomicity problem, or is it an inventory problem for L2 arbitrage?
And that's actually excellent question. So here maybe I just underlined one fact that in those studies, we simply estimated arbitrage that can be exploited. So it's not the arbitrage that people are already exploiting. This is simply what's there and how much time is there. So the question is, why is it so long and why people are not doing it faster? I mean, there are two things. One initial concern was there were not too many well-known AMMs running on the rollups like Uniswap or Curve. Yeah, they are just entering that area. And the second thing is the liquidity. It's still limited at some rollups. So even if the price differences are big, they maybe represent 20 bips of a trading volume. It's still for a big arbitrages running, I know, $1 million companies. It's small, small cake. But I mean, but it's growing. So the trading volume is going up. So I expect that we see those opportunities disappearing faster.
Other questions?
I guess the question is like, why is ZK Sync seems to be always like lagging or have the greatest price difference? Is this a function of liquidity on the chain?
Yes. Yes, but there are also some deeper reasons behind that. So simply those rollups you can see here, they are optimistic rollups, whereas ZK Sync, it's the zero knowledge rollups. And simply optimistic rollups, they manage to have more liquidity because for them achieving EVM compatibility is easier. Whereas for the ZK rollups that you want to be EVM compatible, it's more difficult to develop EVM, and that simply resulted to the fact that those DeFi protocols came there later. But I mean, what you will get from the ZK rollups versus optimistic is a faster finality, especially when the sequencers become decentralized. So there are always some trade-offs.
All right, let's thank Chris.
Good.
Can I share my screen in Zoom?
You can just share it, share it via the dongle, and then we'll use Zoom back. And there's both mics will work, so just, yeah, you can turn that on when you want it. I think this one's already. Our next speakers will be Daning Svi, who's a data scientist at Flashbots, and Barak Oz, who's a PhD student at Technical University Munich.
Is it good now? Okay, perfect. Cool. All right. So yeah, welcome to our talk. This is going to be about this latest paper we have done with Danning from Flashbots and Thomas Thierry from
I'll need to enable it. There we go. We're back.
Okay. All right. No. Sure.
Yeah, just try it.
Okay.
Can you share the slides with my Flashbots email?
Yeah. I think I shared it.
I'm gonna send on Telegram.
Oh, okay. You got it?
Not nervous anymore.
More crowd. Better.
Okay. All right.
Okay.
Back in business.
Okay. Yeah, yeah. Okay, then we can restart. So this talk is going to be about who wins Ethereum block building auctions and why. And this is a paper we did with Danning from Flashbots and Thomas from Ethereum Foundation. And today we're going to introduce you our findings and so on. So the Okay. Oof. The charts are not showing up, I guess. Oh.
Let's try again.
Let's try my computer again. Okay. Okay, it looks good. All right, I'm starting for the third time. Hope this will be the last time. But yeah. How should we do this?
What was the problem? Was that mine? The graphics weren't showing up for some reason in the PowerPoint. If you save it as a PDF and share it, maybe that will retain it.
Can you join here from Zoom?
I can send it.
Oh yeah, try joining the Zoom meeting and sharing your screen locally.
Okay.
It's too much top level secrets.
That is so bad.
Okay.
Awesome.
Where is it? It's sharing now.
It's sharing.
Sharing? What's this?
All right, we're going to adjourn for 5 minutes while I contact IT. So feel free to grab a cup of coffee.
Yeah, okay, then you figured it out.
The coffee break has been canceled due to technical expertise. Woo!
Let's go.
Okay, I'm gonna do this. This is the paper. Okay, and let's just jump in. Perfect. So yeah, we kind of all know that the MEV Boost market is dominated by 3 builders. Well, back in the days when we did the study, right now 2 builders. But like if you look at their profitability in terms of like their profit margin from each block and like their total profits, and then put this into like a bubble plot, which the size of the bubble also shows like their market share, we get a distribution like this, which we have like Titan, Rsync, and Beaver kind of having these larger bubbles. But we also see these other builders who are like these Anon guys, or like I Can Has block and Thank You for the block, which have much smaller bubbles, which indicate that they have like much less market share, but they're pretty profitable. So then like we know that like the market in its current shape with these 3 builders dominating it is vulnerable to censorship, and we kind of need to have to promote competition in the market or come up with these like censorship resistance preserving solutions. And the point of this paper is like, okay, let's try to understand how do these guys actually win the auction and how they become profitable. And we think like there are different features for both of these aspects, and that's why like we break the question into these two parts. And before jumping into our analysis and results, let's briefly remember how the MEV boost auction was working. And like how you win the auction actually. And what we know is that from a builder's point of view, like let's say this is t minus 12, so 12 seconds before the block is proposed, the guy has his mempool view, and transactions over time come into his mempool, and each transaction simply pays a transaction fee, so like brings a value to this builder. And we know that this transaction fee plus some other factors like how much profit margin the builder wants to keep, the time in the slot we are, and like subsidy strategies or like other builders' bids kind of get all put into this bidding function, which then simply like outputs the bid that the builder places on the relay. And we know that over time, builders observe other bids and reflect their values because more transactions come into their mempool, maybe through exclusive channels. And at the end of the day, the proposer simply says, okay, I want to now propose this block, so calls this get header endpoint, and this simply returns the highest value block to the proposer. And of course, like to understand how the value simply like increases like this, we need to understand, okay, like where does this value come from? And we know that, yeah, this is coming from these transactions, which are like enumerated right now. But of course, every transaction is not the same. These transactions have different objectives, potentially different transparency levels, whether they were seen in the mempool or exclusively relate to the builder. So then we need to really like identify, okay, like what transactions bid for Ethereum block space today. And then it is going to show our taxonomy for different labels that we introduced. But our main methodology for the paper is simply it has two parts. We first break down the MEV boost market. So like we decompose it into three parts, like first an overview of the whole market, then looking into specific order flow labels and their like significance. And then finally, we identify different builder strategies. And the whole point is we try to find those features which are associated with being successful in the auction, which means that like, does it have any meaning for winning the auction, like gaining market share, or does it help you with keeping profits? And yeah, this will be the final results that we will share with. So let's start with the MEV boost decomposition. So first we look into the builder market. And the first slide that I'm going to show is just going to be focusing on BRT, or Beaver, Rsync, and Titan, and you will see this acronym throughout. And first, let me just put out these three charts. And the first one is simply showing their market share over time. And yeah, we know that this is increasing. We find that like on a daily average, they have the 80% of all blocks produced, but this is right now around 90%, I guess. What is more interesting here is potentially this cumulative profits over time. And like this green line is standing for Beaver, the orange is for Rsync, and purple is for Titan. And we see that like Rsync, although having a higher profit, higher market share than Titan, seems to have less profits here. But of course, take this with a grain of salt, because this is only looking at the on-chain profits. And like if you're an integrated builder potentially profiting from your searcher, well, then this is not currently accounting for that. And then the other thing is, of course, a builder may have payment for order flow deals with providers. So then, yeah, you might be making this much on chain, but you might also be paying back to the provider. So this number may not be super accurate, but it gives us an idea. For example, you can see that like Titan really just takes off from this February onwards, and Danning is going to share a chart about why that might be the case. And one interesting thing here is that if you look at their daily profit margins over time, Beaver and Rsync have this more consistent lines every day, but Titan actually has like more dips, like more lows, or even days with negative profit margin overall. And we think this is because like Beaver Build and rsync are known for like running their own searchers, so they have this consistent stream of order flow coming, whereas Titan is more dependent on external providers, so the order flow may not be as consistent, so then they might have these like more fluctuating profit margin over time. And if you look at other builders as well in our study, which like covers from October 2023 to April of this year, so like a 6-month period, we see that like 10 builders overall have around 1% profit, 1% market share, and these 10 builders build around 97.6% of all blocks, but they only actually earn around 83% of the whole profits, which means that there are builders outside this top 10 which have small market shares, but they're actually good at making profits, which is also what we show in that first chart. And the rest of the charts, at least in this presentation, is mostly going to focus on the top 10 builders, but actually in the paper, in the appendix sections and so on, you can find the metrics for the other remaining builders as well. So now Denning is going to continue with our taxonomy for the order flow labels.
Right. So we built a system to label out the composition of different aspects of the transaction on a transaction level for these 6 months, all the blocks on Ethereum. We have two, I guess, like separate type. One is transparency labels, one is order flow labels. And so transparency label really is to indicate how private or how exclusive the transactions are. We're using basically the Flashbot's mempool dumpster open source data. Whenever we see the transaction was included in one of those public mempool source, we're labeling it as a public signal. And for any transaction that was not seen ever in any of those 6 mempool sources, we'll label it as exclusive signal. Caveat here is that it doesn't mean it's really exclusive. We don't know how exclusive it is. It could be private to maybe 1 or 2 searchers or to multiple builders, but it was never seen in the public mempool. And we specifically labeled out OFA bundles aside with these two labels because we think OFA bundles are kind of like different. They are neither a public transaction because usually the user transactions are sent privately towards a OFA endpoint, but they were seen by some searchers. So they are somewhat public to the set of searchers who are searching on those platforms. And particularly, for example, like MEV blocker, they are committed to be a permissionlessly, endpoint. So any searcher can potentially basically subscribe to their stream. So it's somewhat public. We try to identify them separately from public and exclusive. And so for order flow labels, we have this 7 big categories, including MEV, Telegram bot flow, solver model, SEX, swap flow, OFA bundle backgrounds, and other. So for MEV, we had a breakdown further to identify if it's atomic arbitrage or non-atomic arbitrage or sandwiching or liquidations, combining with a few data sources, including zero MEV and like a few heuristic data set on Dune, and also our own self-developed heuristics for non-atomic arbitrage, which primarily meaning to indicate SEX-DEX arbitrage. And for Telegram bot flow, we have a data source that covers a wide list of the Telegram bots on Ethereum, including, for example, like Banana Gum, Maestro, and others. Solver model, we covers 1inch Fusion, CowSwap, and Uniswap X. We separate them from the retail swaps because they have a different type of submission process or life cycle compared to all the normal transactions that are submitted by the retail users through wallets. And SEXs are basically all the centralized exchanges who are sending deposits to their users when the user are basically trying to deposit on chain. For example, like Binance and Coinbase's. Swap flow includes first retail swaps, which we are basically trying to identify based on the known routers for the major DEXs or DEX platforms, DEX router aggregators as well. And for other swaps that we are seeing, potentially generically under a Uniswap V2 router or other unknown routers, we will categorize them as just like bot swap. This is potentially capturing also some MEV transactions that were missing from the previous heuristics. and OFA bundle are identified based on the same heuristic we were labeling for the transparency labels, where we basically assume a set of 3 transactions adjacent to each other, where we see user transaction first, and then followed by a searcher background and also a refund transaction. We also extended to consider the case where sometimes the searcher may add their background and refund many transactions afterwards. Mostly we're combining using MEV blocker and Flashbot's MEV share transaction on dataset on Dune. And for all the other transactions that we didn't identify, we'll just simply default to the public or exclusive signal label. So here are some results or data that we observe. The first slides here that we are looking at is basically looking at the transparency label distribution measured by, on the left side, the MEV value, which means like, just to define MEV value here quickly, we're calculating basically all the gas priority fee and also the builder tip, which is basically forwarded through the Coinbase transfer method in MEV Boost. So combined together, we call them MEV value, which are basically the value paid out to proposer. This may not mean the whole MEV value that the order flow contains, because some of them might be actually taken or pocketed by the builder or the app owners or other sources. And on the right side, this is a gas share. So basically how much gas does these transactions consume, or basically how much block space they take. And the interesting observation here first is it kind of follows a Pareto rule, where you see that the majority of the transactions who are basically labeled as public signal, as the green-blue, are taking up most of the block space, maybe more than 80%, while contributing much less values compared to all the exclusive signals. So basically we're seeing like exclusive signal are providing 60% of all block value, while only taking up 19% of all the block space. And if we look at all the across all the blocks fluctuates, they constitute 71% of all block value in more than 50% of the blocks. And of course, we also see that OFA bundle overall is very much less adopted here, and we barely can see them in the chart. And then the next one is to observe the transparency distribution across different order flow type, across transactions, or and also how much acquisition in terms of like private order flow across different builder on the right side. So on the left side, we're seeing that it's interesting from bottom to the top. We're seeing that the order flow, including non-atomic ARB and other exclusive order flow, sandwiching, atomic ARB, liquidation, which are all MEV transactions, they are pretty much mostly all exclusive signals. So searchers are by default sending those privately towards builders, so to not be seen in the public mempool to reveal their strategies or being attacked or by other people. Another big category we see here is Telegram bots, where they are also showing more than 90% in terms of the value are being sent exclusively. They are able to do this because the users are sharing private key with the Telegram bots, or basically the Telegram bots generates a wallet and preserving the private key for users, submitting transaction for user. That's why they are able to basically submitting transaction for user and decide for user. And besides that, we also see solver model, which is when user goes to potentially Uniswap, 1inch, and CowSwap, they have the options to basically settle their transaction with the solver model, where a bunch of solvers are trying to compete to quote for the best price across different liquidity on DEXs, AMMs, or even like private market makers, where we see that the submission for all these solver model are also dominantly private. And among the rest of the order flow, for example, like retail swap, we can also see around like 15, more than 10% adoption for private order flow, potentially because users are using private RPC to avoid some big slippage causing by the MEV actions. We also see SEX deposits are pretty much all public, just because they're naturally, immune to any like price relevant MEV strategies. So on the right side, we're seeing the builder list from bottom to top ranked by their market share. So the lower they are, the higher market share there are. So Beaver is the highest market share builder here. And we're seeing that generally the builder with more private order flow or basically exclusive signal are going to have a higher market share. And we see that like BRT, the top 3 builders are receiving the highest relative value from exclusive flow, exceeding 65% of their total. And among all the remaining builders, their value can range from 1% to 91%. So here is the next chart where I call it like an order flow treasure map. I think this is an interesting chart for everyone because this is, we're trying to basically break down all the transactions by order flow type, how much MEV value they are paying or contributing towards the proposer revenue, and comparing with the chart on the right side, how much gas share actually they are consuming, or basically how much block space they are consuming. For user, it's interesting, basically, this is how much you are paying and or potentially you might be overpaying. For the apps, this might be potentially how much value you're left out on the table, or for anyone or any like team is basically trying to acquire more order flow to increase whatever their builder market share or any other potential value. This is the customer you would want to go after, right? So just to examine the charts here, we're also seeing somewhat like a 80-20 kind of divide. You see the red and the pink are basically retail swap and other public flow, which constitutes around like 70% of block space, but yet they're contributing around like 30% total of MEV value. Meanwhile, we're seeing that the most prominent MEV value from this 6 months data period, it comes from Telegram bots, which is a lighter blue on the left side of the chart. And then the next one as a top value MEV flow is sandwiching. And then next is bot swap. And then the next is non-atomic arbitrage. And among them, you will see that sandwiching and non-atomic arbitrage are really taking up at most 2% of the block space while contributing around 20% each for the MEV value. And we see Telegram bot flow and MEV order flow cumulatively contribute 51% of all the block value while consuming 10% of total gas. And more valuable flow is exclusive submitted and blocks are filled with less valuable public flow. And we also, on the right side, we have a breakdown of all the top builders and their order flow composition breakdown of different type. And we're pretty much seeing that everyone has a various source of order flows, a good diversity of order flow as being the top builders. And the BRT, so basically the top 3 builders, they have significant value coming from the valuable order flow, meaning Telegram bot, sandwiching, bot swap, and non-atomic arb. So here is just another timeline view of all the top 3 builders and what are the significant exclusive order flow provider for them. So basically, when zoom into all the exclusive order flow provider, we identified this 7 order flow providers as the top one of contributing the value. So Jerry from Subway, which is the most famous and like the most successful by profitability, Atomic Searcher, and Banana Gun, Telegram Bot, and OFA order flow from Flashbots Protect and MEV Blocker, and Mainstream Telegram Bot, and SCP's non-atomic ARB, and Wintermuse's non-atomic ARB. And we can pretty much see it's very evident that the yellow, which is the SCP flow, are only, seen in the Beaver blocks, and also contributing quite a high amount of MEV value, which is around 20%. And the darker yellow, which is the Wintermute flow, are only seen in the rsync blocks, contributing around 20 to 40% of MEV flow. And we also see that like all these 3 top builders, they all have Jared flow, Banana Gun flow, and other OFA flow. But we observed that like the orange, which is the Banana Gun flow, somewhat spiked up around February in Titan's block particularly, which in correlation with their spiking up, profitability charts, which is a dotted line here. Usually cumulative time series is a chart crime, but here I think it's interesting for us to like observe this correlation. So yeah, and Brooke will continue with more summary about the builder strategies.
I had to stop. Okay. Okay, this is going to be fast. All right. So what we try to do then is that, like, after measuring the significance of the order flow labels and these builder strategies that I'm going to show, we will all tie it to into like finding which ones are correlated with winning the auction and which ones are correlated with making profits. But simply to go over these builder strategies, we identified 4 of them. One of them is block packing. So we look at like which parts of the block provide or like provide what kind of how prominent value to builders. And we have like top of block indicating the top 10%, body of block the 80% in between, and then end of block is the bottom 10%. And we see that top of the block is providing the most significant value to all top builders except Penguin. And like when we look into like, okay, like what resides in top of block, we see that more than 50% of all exclusive transactions are residing here, providing around 88% of the all exclusive value. And we also see, interestingly, that Titan, Gambit Labs, and Penguin also have a relatively significant end of block value, which could indicate that they allow searching at the end of their blocks. We also see that on the subsidy profiles, some builders like Flashbots or Builder 69 are really not subsidizing, whereas some lower market share builders adopt this subsidy strategy. But we see that profitability is usually also increasing with market share there. And then Danning already talked about exclusive order flow access, so I'm going to skip over that for now. And then we also have some metrics about latency and bidding, and specifically strategies such as cancellations. We observe them to be adopted by, again, by these more successful builders. And if we come to the results, the first result we find is that the diversity of order flow correlates with the market share. So builders who have more diverse order flows, which we calculate using Shannon entropy, also have higher market shares. And this could be potentially because these builders get order flow from different providers, which simply make them more competitive or competitive more frequently than a builder who only gets order flow from their own searcher or maybe from like a single source, so they can't win the auction that often. And we see that like these smaller market share builders, they usually have like a single order flow label, which is extremely prominent for them. And yeah, we see that this is then negatively correlated with their market share. We also find that 55% of the builders have this provider, which we call as an exclusive provider, which is a provider that is only significant for a single builder. These like columns with a single color cell indicate this. We use some machine learning models to detect this. So like you can see like the classic Beaver built SCP or rsync Wintermute here, but also other searcher and builder integrations. And we see that builders who have such kind of providers are actually more profitable in general than the builders who don't, because the idea is that if you have order flow that the others cannot access or don't have, then you can keep profits and you can simply become more profitable. And then finally, we use all these features that we initially identified and looked at which ones are correlating with market share and which ones are correlating with profit margin. And we see that there are a lot of overlaps, and actually there is a positive correlation between these top 10 builders' market share and profit margin as well. And like the result we converge into is that there is this chicken and egg problem, which also other works have highlighted. That is like, if you want to be profitable, then you need to access order flow from these providers, which are usually not really providing order flow to everyone else. So it's like kind of differentiating you, but then only builders with high market share can get access to such order flow. And yeah, in the paper, we discussed some solutions for protecting Ethereum's censorship resistance and neutrality, which Mike also mentioned. And yeah, again, I'm just summarizing our contributions here. And the paper will be featured in AFT this year. And this is the archive link for the paper. And that's going to be all for now. Thank you.
All right, any questions? Okay, well, I think I will send any questions that come up to the coffee break.
Max had a question.
Max has a question? Where's Max?
I have a question. My understanding of the Telegram bot arrangement is that there is some refund that happens. Do you think that your methodology is overestimating the importance of Telegram bot flow because it just counts like what you can see on chain.
Exactly. That's a limitation that we also mentioned. So like the Titan profits, for example, we showed that's for sure an overestimation because they probably pay back some amount. It's hard to, I guess, estimate like what is the ratio there, but definitely that's like a nuance that we need to consider, that like that on-chain payment that is done by, say, Banana Gun to Titan is definitely not just Titan keeping all of it. So yeah, it's definitely like an overestimation.
Do you think there's some way to maybe tease out what the actual fair value they have for the block is based on their bidding behavior? Or
good question. I think it's like we need to look at the frequency of this order flow appearing in blocks and like when it occurs, and potentially this might indicate something about like how much they value, or like what is the significance of that order flow. But yeah, I don't know. I have to look into, like, one thing I looked into was especially for some subsidizing searcher builders, like why are they subsidizing? And we actually see that when they have their searcher flow in blocks, they subsidize much heavier than when they don't, which then if you take the difference, you can think it as, okay, this subsidy difference could potentially be their searcher profits, upstream.
I think there's two layers of answers to that question. So like, first of all, if this always going to be a closed door deal and the payment is happening off chain, then it's impossible for us to really identify what C value our distribution are. But also like, what is the fair value? I think even right now with the basically the integration or like the payment for order flow between this kind of arrangement, there may not paying the fair value. They might be overpaying until there might be competition between the builders who are basically handling the order flow. So I think that can be also interesting with some like redistribution, refunds kind of research as well. Yeah.
All right, let's thank the speakers. Okay. And if the panel could come down and start getting set up.
Wow. I'll introduce you and I'll give you this. All right, up next we have our panel. The panel will be moderated by Quintus Kilburn, who's a researcher at Flashbots. And Quintus, I will have you introduce your panelists.
Right. Thank you. On the right side of the ring.
God damn it.
Okay, so earlier in some of the talks today, we have heard mention of multiple concurrent proposers, but we haven't gotten too much into the topic. And so in this panel, we'll try cover like the proposal or the set, like the class of proposals, I guess, in that direction, give people some context, and then sort of discuss the MEV side of multiple concurrent block proposers. There's obviously like a consensus challenge to this as well, and Max might mention that a little bit. But today I'd like to focus on some of the incentive issues, how this impacts validators, how this impacts like users accessing the chain, etc. And so I guess if people don't know, Phil to my right, who will introduce himself when it's his turn to speak, I guess, and then Max to my left. And I think the rough divide today is that Max has been pushing the multiple concurrent proposers direction, and I think Phil has some reservations, and so that's going to be the setup. But hopefully it'll be a constructive discussion. So maybe just to get us started, Max, can you just sort of frame multiple concurrent proposers and explain the setup?
Yeah, I mean, just to be clear, I'm not trying to push anything. I just think that this is what we should do to make Ethereum better. And so I'm presenting the idea and why I think it's a good idea to make Ethereum better. And if people disagree with me, then we shouldn't do it. And if people agree, then we should do it. The basic idea behind multi-proposer is like 2 years ago, I was sitting with Elijah, who's one of the co-authors on the initial censorship resistance paper, and we were trying to figure out how to solve basically toxic flow, and in particular, the element of toxic flow that gets forwarded directly to the proposer through MEV-Boost or previously MEV-Geth. And so we wanted to figure out how to make that part of the auction that's currently going to the proposers actually go to the app so that we could create lower spreads. And so the first thing we thought about was, let's do an auction. But it turns out that doing an auction is actually quite difficult on chain because say you have a $1,000 item, the proposer can censor all competing bids, put in a stink bid for 1 cent, and win the item for 1 cent. And so in order to stop that, you have to put extremely high proposer tips, and you end up giving away a lot of the value from the $1,000 item to the proposer. So our solution to this was basically, instead of one proposer, let's end the proposer monopoly, let's make multiple proposers, and then make more than one way to get on chain, and then hopefully no proposer monopoly exists, and we can hold an auction again. And we like auctions a lot, so we think that's like a very good direction for DeFi on Ethereum to go in.
Okay, cool. That's I guess the motivation for the problem. And now, if we look at the last couple of years, people have been trying to address like the short-term censorship resistance of Ethereum for a while. And that has all come in the form of like inclusion lists of various forms. The most recent proposals are like Fossil, which people might be familiar with in the audience. Could you sort of contrast the MCP approach to what Fossil's been trying to do?
Yeah, so I think there's two things. So Fossil is actually not too far off from what we're talking about. But over time, the inclusion list proposals have gone from one inclusion list from the proposer, which gets included in the next block, to now multiple inclusion lists from not necessarily the proposer, but from the inclusion list committee that now get included in the current block. And so we actually see the inclusion list proposals kind of trending towards multi-proposer. I think that's probably fundamental because the only way you get censorship resistance is by having more than one choke point to get onto the chain. So I don't think they're that different. There is a key difference in that the implementation of Fossil has a proposer who has some elevated privileges. So the Fossil, we call them the view canonicalizer. They have some ordering power, and in particular, they can act later than everybody else, and so they have last look. And so I think that's the key difference between Fossil and Braid, which is the design that we've suggested, which is that Braid, everybody proposes at the same time. I know Phil will quibble with that a little bit, but at least in the same synchrony round, everybody proposes. And that's the difference between Braid and Fossil.
Okay, so just to recap, we're trying to achieve short-term censorship resistance. The way that all of the approaches are trying to do this that have been proposed so far has been involving multiple actors sort of giving their view and that being included by the chain in one form or another. What distinguishes the MCP approach is that we're trying to have all those proposals from the committee sort of happen at roughly the same time. And the reason we want to do this is because we want to take away any privileged power that a specific actor will have. Okay, Phil, can you steelman this approach? Like why, if you're going to make an argument for why we should pursue the MCP direction, what would your justification be?
Yeah, so maybe to give you all a little bit of lore, part of it is it's kind of funny because most of the time I spent sitting in this room was when I was here in grad school working on MEV for the first time. And very early on into studying MEV, this was kind of the first direction I took, was like, can we just have a committee to kind of remove a lot of these issues from the L1 protocol? Funnily enough, I took a class in this exact room to try to figure that out on social choice theory and voting and kind of all of these ideas of compressing these vectors into a single order. So, you know, I have a lot of empathy for the idea. I think the Steelman is kind of exactly what Max said. It's like, why have one input when you can have many, right? But the question is then, what are those inputs and what are the incentives behind them? So I think that's where the Steelman breaks down.
Okay, and then Max, I realize there's like two components to the MCP. There's like actually can we implement this in consensus in a way that preserves the properties that we care about? But leaving that aside, assuming we have the eventual consistency we want and these kind of things, what do you think are the sort of the most reasonable critiques of the direction you guys are proposing?
Yeah, I guess if we kind of assume the hardest part about the consensus, let me just say that, is basically, can we get synchronous release, or are the timing games too bad, or are there games you can play with the attester as well? And so I would say, if I'm like attacking the idea, I think it's like, can you demonstrate that that is solid and that we can actually achieve the desiderata that we have there for synchronous release? So I think that's definitely a potential failure point, but that's on us to prove that we can do it in the system that we were describing with Braid. I think there is definitely a lot of legitimate critiques of each of the ordering rules. In terms of my personal perspective, I'm spending more like 70% of the time on Braid, the consensus rule, and I hope that there will be a lot of discussion and input on what the ordering rule looks like in the end. But certainly if you choose the wrong ordering rule, you could get worse outcomes, because the ordering rule is incredibly integral to what game we're actually playing. And if the game is wrong, we could get spam, we could get all kinds of undesirable things that we had in like pre-MEV-Geth days.
So I'm going to jump in with maybe two criticisms there. Number one, I actually don't agree that the last look or the release is the critical problem. I mean, I think that's one of the many, but I think there's also like, how do you pay for advantage in the ordering? So can I pay to bias the ordering in my direction, even if I don't learn the ordering first? I think that's one example of another, what I call like a perturbation vector in the ordering, which are super important to quantify and study. So I think to say like the last look is the big problem, you actually need to quantify both of those things and then compare them, which hasn't been done for any of these proposals.
Well, I think before we continue, I think this is a good discussion to have. Some people might not be that familiar with the ordering rule discussion and why that's even important. So could you just like explain what that is and just high level what some of the proposals are?
Yeah, so there's two stages here. We have the consensus stage where we have multiple proposers. Each of them propose a partial block, and then we zip up all the transactions with a union. And then you apply a deterministic ordering rule on that unordered set of transactions, which spits out an order. And is that sufficient explanation, or is there more?
That's sufficient. And then can you just cover, there have been two like major proposals so far. Can you just like touch on what those are?
Yeah, so there's two proposals. One of them is basically you just sort by priority fee in descending order. So you just execute the highest priority fee first. And there's a modification of that called MEV taxes, where you are able to tax a certain percentage of that priority fee and send it to the app itself to distribute, that Dan Robinson and Dave White put out. And then there is another proposal, which is also a modification of priority ordering that I call execution flags. And it basically allows transactions to set a flag of, I want to touch, the UniV5 pool trading ETH-USDC. And then when the ordering rule hits the first execution flag, it pulls all the transactions that are trying to hit that pool and executes them as a batch.
Okay, cool. I think that's pretty good. And then just coming back to Phil's point, do you want to just give a quick recap of that and then we can continue from that point in the conversation?
I mean, the point is, so for many MEV opportunities, what matters is who can touch the state first. That's a broad class of these opportunities we're talking about. Certainly sex-dex arbitrage is conditioned on that. And just because you can't control the full ordering doesn't mean you can't bias it in your direction. And economically, all you've done then is taken this deterministic arbitrage and moved it to a probabilistic arbitrage, which in general, fewer people know how to price, fewer people know how to bid in the auction in. This was kind of the core of Malesh's talk, and they can also exercise more pricing power. So that is one important dimension, basically against which none of these new L1 proposals have been analyzed, which I think is super, super critical for future work.
Yeah, I think in some ways my goal isn't to make Uniswap v3 or v2 work better, because you would actually have to change the app for it to work better to take advantage of the new tools that we're providing. And so if you're kind of in this world where all of the apps look exactly the same as they are today, and then we give the app developers a bunch of tools and they say, actually, we already like sold all our curve and like have a couple houses in Australia, then it doesn't matter because they haven't done anything. So the app developers are going to have to uphold their end of the bargain, which is to move apps to a more order agnostic situation, which I think they will do. And there's plenty of companies that are already trying to do this even now, even though they're severely restricted by the L1. And I think that we would see a lot more movement in that direction if we gave them the tools to do it. So it doesn't necessarily have to look the same way. We can imagine what can be unburdened by what has been.
I mean, no, I think to me, an ordering agnostic, system is almost like laughable from the context of MEV. Like the ordering will always matter. All you can do is make it agnostic to the L1, which basically means you're moving that same game just to some other part of the system. So rather than having the centralization at the L1, you now have it in the UniX auction, for example, which is then influencing your blocks on L1. So I don't think that's actually meaningfully improving the situation.
I mean, an auction inherently is completely order agnostic in that it processes all the bids and then it computes the highest bid.
Not if it's an auction for who goes first, then it's not agnostic to the underlying order that it's deciding, because that's how you pick winners and losers in an exchange, for example.
I think maybe a good way of having this discussion is to focus on like an application. So we talk about order agnostic applications. We can think of something like, I think CalSwap might be a good example. You can build like an on-chain batch clearing kind of mechanism. Does that make sense?
Even CowSwap is centralized, right? It's exactly what I'm talking about. They've taken this MEV game and they've moved it to this permissioned off-chain system that they're running in a data center. So they haven't in any way made their application ordering agnostic. They're just deciding that ordering on a centralized component, basically.
Yeah, but
it's
why?
ordering agnostic only with respect to the L1 semantics, which doesn't actually change the economic power distribution or the centralization of the MEV in your system.
But Phil, why did they do it off-chain? Because they couldn't do it on-chain, because they didn't have the tools to do it on-chain, because they didn't have censorship resistance.
No, they can't do it off-chain because they're leaking information on the user quotes to a network of permission solvers. And the more solvers you leak that information to, the worse outcome you have, because essentially you're diluting the value of the information by simply signaling the bid into the auction. And to deal with that, they need to use things like proprietary fake bid spoofing and permission lists of like policing their solvers manually. And even if you had all the flags in the world, you can't move that off-chain because someone still needs to police and create those fake transactions that basically is a trusted party. Their application is not actually designed to be decentralized, which, by the way, side note, that was one of my original criticisms of them in like 2017.
Yeah, I think Phil and I have a fundamental disagreement about how important noise trader information is. I tend to think that noise trader information is noise, so it doesn't convey that much information, but it certainly conveys some information. And so there are definitely trade-offs there. You could feasibly do threshold encryption and then do a batch auction without revealing information, right? Maybe in 10 years when we have the FHE to do it.
Okay, so threshold encryption has some other gotchas. So I can give you my kind of counter view, my thesis of MEV, which is that there's a few things that matter. The first one is actually looking at the real MEV game of how economic power expresses in the system. So there's two trading firms, they want to compete, who wins and why. Do they use latency? Do they use spam? Do they use an auction? Do they use capital? What's their advantage? What's their edge? What's their competing game? So that's one example. And I think you have to look at it through the lens of statistical perturbations. Just looking at deterministic ordering is not enough. So I think that's one bucket. And I think the second bucket that becomes more relevant here is for Ethereum and for the system. What I think is really important are four different properties of block building. And that's what determines whether we end up in a decentralized cryptocurrency or not. So the four properties are: number one, permissionlessness. You need to be able to join the system and express your economic value at any time. Number two, distribution. The system needs to be logically and technically distributed across many computers and many nodes. Number three, geographic decentralization. And I'm not talking about the Solana definition where you have one node in the US and one node in Europe. I'm talking about a protocol that's designed to minimize the additional profit from colocation. And the fourth is the ability for a neutral builder to enter the market without a substantial barrier. So that was something like Malesh's talk was addressing earlier, where certain structures kind of bias towards incumbents. So I think those are the really important properties. I think something like threshold encryption, it doesn't satisfy the geographic decentralization because of this last look issue, because if you co-locate, you can run the protocol much more quickly, et cetera. And therefore, it's a centralizing market force on block building.
I think we agree that permissionlessness is incredibly important for the ideal block building world. And I think it's also very important for applications on chain. And that's why I care about censorship resistance, because if the proposer can tell you that your bid, your signal of what your demand curve is not getting on chain, then they've effectively prevented you from participating in the system and expressing your value. And they can do that for their own gain. And I think that's like an incredibly harmful thing that really kneecaps a lot of app designs that we could see on chain.
I mean, I think we all agree censorship bad, right? And there's like time horizons of censorship. Like ETH today is censorship resistant if you're willing to wait. MCP is not censorship resistant on a short enough time horizon because you have latency actors that can front run you arbitrarily, for example. So I think we're like splitting hairs over like how fast does the censorship need to be. I don't know if we have consensus among that as a space. Certainly, I agree censorship is bad and we want people to be included as quickly as possible. And we want many voices to participate in this. I think where we disagree is I don't think a committee is the right structure to pick ARB winners and losers because it opens you up to manipulation of that committee, which is a centralizing force on the committee rather than a decentralizing one.
But why is it better to have one person pick ARB winners and losers than the committee?
Well, because, I mean, if you have one person pick or a committee, they're all going to be listening to the kind of economic powers that be, right? So what you want ideally is like efficient outsourcing of that, which is kind of the PBS thesis. It's not like the validator that's meaningfully building the block or censoring. And in, for example, a Suave or programmably private model, it's even less so because they may not even see the contents of that block. What matters is decentralizing the actual building process, right? If you have MCP, yes, you've said we've taken multiple inputs into this last step, but that doesn't necessarily mean multiple economic parties are involved in the building. Like if SCP has better latency to all these nodes, they can still censor you for some definition of censorship. They can front run you every time. They can collapse the network to like their own validator nodes because they're making more profit per block than anyone else. And I think those are also like very dangerous censorship vectors more than the technical, like, are you included this block or not?
Yeah, I don't really see how any of those things are specific to multi-proposer. I'm pretty sure that SCP, if they wanted to, has the economic like advantage to be able to give a profitable agreement to a bunch of node providers today. In fact, this is like not SCP, but this is like something that has happened before. There have been offers that have been made by builders, at least that's the rumor, to partner with validators. And so like, I don't see how that's a fundamental issue with multiple proposers.
Well, what multiple proposers does is it shifts the game more towards a latency game because your latency among those proposers is like an extremely relevant variable in how much each is able to extract, and also the efficiency with which the various ARB firms can extract MEV on top. So you've basically taken like, what you have in MEV is you have a three-point pyramid. It's either auctions, latency, or spam. There's no other known way for these trading firms to participate in the network and get an advantage. They either optimize their latency to various points, they spam people in the network, or they participate in an auction. Those are three things we've observed in practice. If anyone knows a fourth, I'm always open to adding to the model, but I haven't found it yet. So the question is like, how are you moving the dial between these things for these firms? If you're moving it more towards latency, I'd argue, if anything, you're centralizing the network more in the long term.
Yeah, but I don't think it's that clear that this is actually more latency heavy or more weight on the latency, because currently you have timing games which are based on you get an extra, however many milliseconds of proposer monopoly. Here in this new system, you would have an extra few hundred milliseconds of ability to add transactions, which is valuable, but not necessarily as valuable as an extra 100 milliseconds of proposer monopoly. So I think there's definitely competing effects, and
well, no one's done the math right because the surface is large. Like you can bribe any member of the committee, you can take action in any member of the committee. Depending on your ordering rule, it may be the case that you even have one pivotal node in your ordering, and like how you kind of, like I said, like all these like kind of impossibility theorems from social choice, right? Often like you have pivotal nodes in the network where bribing these nodes or impacting these nodes is much more profitable. So I think it's plausible that you're right, but I think someone has to actually do this math, which no one's done yet.
Yeah. I think it's important. Well, we're just getting started on it. I think it's important math. I would just say I want to just clarify that we're not thinking of this from a social choice theory perspective, because in social choice theory, you're fundamentally constrained by, you don't have like a strength of preferences. And so this is like a situation where we have tips. And so we do have a little bit extra information that lets you get around some of those impossibility results.
I mean, that's not true in like quadratic voting and many other, right? Like there's all sorts of voting systems that let you express strengths of preferences.
Yeah, but this is a situation where we're not trying to make ordering decisions based on the ordering of each of the individual nodes at all. In fact, we just ignore that information of what order each of the individual nodes put stuff in. We're going to not take that into account at all. And so all block space is going to be fungible, basically. Block space in one proposer's block is going to be the same as block space in another proposer's block, because we're going to zip them all up into an unordered set and then apply the ordering rule, which does not depend on any ordering input from each of the proposers.
Okay, I want to hop in here because I think we're running low on time. I'd like to go back to something which came up earlier. So my understanding, like broad strokes of the discussion so far, has been that the multi-proposer potentially addresses some of the censorship issues. Phil's made the point that there are many other. One, it may not be the case that this is always true, because there might be different dynamics that evolve that favor certain players over others and sort of erode some of the properties you want from censorship resistance, but also that having multiple proposers impacts other properties of the network that we might care about, like geographic decentralization. But my question then, and you did mention some of this, but I'd like you to elaborate, what is the alternative vision? If we don't pursue this committee-based vision, can you elaborate on how we get some of these censorship resistance and related properties in the network without relying on a committee?
Yeah, sure. So my opinion on all this is everyone in the space should be working on like really one problem at this point. And that problem is, let's take a look at the tree, or the DAG, or whatever you want to call it, of economic messages and computations that go into building an Ethereum block. And how do we make sure that this process is actually meaningfully including the input of many parties? Now, it's not enough to just take the technical protocol and say we add a last step that aggregates the input of many parties. To me, this makes like a kind of error which assumes that the economics will follow the technology, which is not the case. The question is, how do we take this power, which right now comes from the fact that SCP has proprietary kind of algorithms that run on Binance, comes from the fact that they're renting latency pipes from hedge funds and things like that. How do we take all of these economic forces and meaningfully push power out to the edges of the network, to places in the world where power has not historically existed in the network? And how do we get all of these different parties to kind of be economically meaningful in the block process? I think then, no matter whether it's one entity, one node signing the message, or 50, that's where the censorship resistance is going to come from. It's going to come from the economic diversity and the fact that no one economic party has economic control of the block production process. I think we do that in a few ways. I think one is TEE and other cryptography-based tools, being very, very careful about geographic decentralization and not to introduce latency co-location incentives, but use these tools to allow these disparate parties in the block production process to collaborate and to join each other's input, but having to accept each other's inclusion properties and censorship resistance preferences, and et cetera. So one is to build these tools for collaboration, and the other one is to build meaningful demand basically around the world for transactions that need to be processed in different ways, that need to be processed in different locations, such that to leave these transactions on the table and to leave these people's censorship preferences on the table, you need to pay a cost. And I think ultimately that's where we get censorship resistance. So if you're an app, the question is, okay, we're Uniswap. Like, how do we find more order flow that really needs these properties that we are trying to build for Ethereum, and build this sticky moat inside block building such that we can express our users' power into the system? And I think that's what every dApp should be doing. That's what the L1 protocol should support, is kind of this universe of distributed block building. And I think the key to do that is to make sure you don't introduce co-locations incentives. That's where blockchains like Solana and many L2s, in fact, even many companies in this room, have fallen short in the past and have seen the predictable MEV games.
Do you want, you're welcome to say something, otherwise I have a follow-up question.
Go for it.
Okay, so if you know, putting on my MCP hat, I listen to that and it sounds appealing, but hard to achieve. And I guess on both sides, we have a lot of details we still need to flesh out to be able to have a really concrete discussion. But one of the things that seems to be true if we don't go in the committee-based direction, which includes Fossil and MCP, is that we leave one actor with this like one bit of control, right? Where if we keep the status quo as it is, the Ethereum protocol as it is today, and we have MEV-Boost or like EPB or something very similar, you still have this one proposer who can choose not to build a block. And that's like one bit of control, but a very important, substantial bit of control. And do you think that we can continue with that being the state of affairs? And if we can't, then what is the alternative to using a committee?
Yeah, I mean, it's hard to say. I mean, I think all these questions, they really depend on the specifics of the protocol, right? Like, I mean, obviously, ideally, you rely on as few people for availability and censorship resistance as possible. The question is, what are the trade-offs and what is the most appropriate for building a financial system? I think it is better for ETH as a decentralized system to be in a status quo where there is monopolistic control every 12 seconds, but the economic gain to actually build that block is more widely distributed versus, like, let's say a world where you have many people inputting into these 12 seconds, but you have like fairly geographic concentration on the economic side. Now, which protocol leads to which world? I don't think anyone's done any of that work. So it's like very hard to speculate. Like, yeah, if you have a magical protocol, I think it would be great to not be relying on one person for availability. I actually think this is where these proposals converge. Like, I'm a very big fan of having multiple inputs into a block. I just think it needs to be done in an MEV-aware way, such that the actual merging rule considers the MEV and interacts with the private information in a very nuanced way to actually merge these outcomes intelligently and like efficiently extract and redistribute the value, rather than exposing like kind of a lossy game for people to play statistically against with various other network resources. So I think I'm an MCP bull, but it's like MEV aware MCP, please.
I see. Okay, and then so touching on this MEV awareness, Max, can you talk about like what? I guess we still have some things to define, but what are some of the changes that would be required if we had Braid or whatever MCP implementation we arrive at? It seems like there are important differences around our ability to have, or like at least in my current understanding of Braid, you'd need people to use the public mempool, for example. Yeah, please continue.
Yeah, you don't need to use the public mempool. You can send directly to the proposers. Actually, I mean, we modeled it as each of the proposers is running MEV-Boost. It's just that they're not like running MEV-Boost collude version. So they're each running their own thing, and they're trying to profit maximize for their own block, not with respect to collusion with a large set of other proposers in the quorum. So you don't necessarily need to use the public mempool, which I guess is a good thing because that leaks information, as Phil said. And I guess what should we do in the next hard fork if we actually want this as a direction? We should delay the state root by one block so that it's off the critical path, and we're prepared to move towards state root delay, which will be needed for multi-proposer. And we should start to think about how we can make sure that there's enough bandwidth available. And we need to make sure that we do not give away all the bandwidth to pure DAS in order to preserve some, at least, for the actual chain itself and not for giving away free DA to L2s.
Okay, I'd like to sort of continue a bit more down this line of thinking about external markets for block production. So today, the MEV-Boost auction is relatively simple. We have one actor who has the right to build the block, and they run the auction most of the time, and it makes sense for them to just take the highest paying block. But in this world, it looks very different, right? From the perspective of someone who's trying to land something on chain, there's multiple avenues. And maybe latency, like Phil was saying, is the more important dimension. Have you thought through how this kind of market would evolve?
In terms of the latency games, or
just if I'm running a validator, it's my turn to be one of the proposers. How do I even select what block goes in? Is it just another auction?
Yeah, I mean, you just look at the set of available transactions and you try to include the ones that are the highest expected inclusion tip for you, because you're not getting an ordering tip. The ordering tip is going to be captured by the protocol. And so it's actually an easier problem of like, I'm just looking at the inclusion tips and trying to maximize my expected value over the inclusion tips. And there's some randomness because if I include something that a bunch of other people are including, I have some reduced rewards for that. But still, I'm going to basically look at the available transactions, some of which may be from the public mempool, some of it which may be private, and try to construct the block that I think maximizes the inclusion tips. And I don't even have to care about the order at all. I'm just subject to validity conditions, maximize my inclusion tips.
Okay, but how do timing games play into this? Because someone has to release their block. Someone has to release their block first. There's no true simultaneity. Do you think you see today we see people with incentives to delay their blocks? Do you think this carries forward?
Yeah, I think if we don't do anything about it, then we will see something like that carrying forward. Like I said, I think the timing games, you have to think about what the incentives look like. I actually think currently it's very unaligned behavior not to participate in timing games, because you are basically giving away free money to somebody who will participate in timing games if you don't participate in it right now. And part of the problem of timing games is that the devs set like some 0-second call time for honest nodes. And that was actually way too far from where they should have been if they're like playing a timing game. And so the honest nodes who are playing a timing game are not anywhere close to the dishonest nodes who are waiting 2 seconds. Dishonest, whatever. They're just rational. I think everybody should play timing games. We should push it all the way to the limit. And then the delta between nodes will not be as high as it is today. Like it's high because we're trying to cling on with a thread of social fabric. The social slashing committee will come get you if you play a timing game, which they won't. But just like everybody go do it. And like it will not be that bad for Ethereum. And the difference between honest and dishonest nodes will be going down.
I don't know if I agree that it won't be that bad for Ethereum. I think it harms an important builder vector, which is like then you need timing games infrastructure to participate in the protocol. And depending on what your like returns curve looks like for that timing games infrastructure, like if you spend more money on the latency infrastructure and get more profit or more of a percentage of the network, that's then a very centralizing effect on the validator set.
Well, I'm not saying timing games is a good thing. I'm just saying, given that timing games exists, the best thing to do about it is to let it rip rather than to try and cling on with a social slash.
I agree for participants, but I think for the L1, we should try to minimize it, which is also my perspective on MCP. Like it's rational there for everyone to play timing games and listen to bribery oracles and like play inclusion games and possibly order like offer cancellation modules through like SGX for like, backdooring, ordering into inclusion and blah, 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 blah. We should assume everyone's rational. The question is then, how do we design the L1 such that like we don't get weird degeneration in the protocol?
Well, yeah, I mean, and the core thing that we should do is do missed slot penalties. That's like a no-brainer because not having a missed slot penalty is contributing to timing games being much worse in that we're getting more missed slots in equilibrium from not having an appropriate missed slot penalty. And it's just so funny that you try to work on ETH and then they tell you actually like you can't have any compute because we're going to run everything on a Raspberry Pi. You can't do anything that involves timing and you're not allowed to slash anybody. So like what is left? Like what are we, and you can't have a committee anymore either because Phil said so. So like what are we supposed to do? Like just sit here and just like do out of protocol stuff? I don't know.
I'm not saying you can't have a committee. I think it depends on the protocol. Like the whole blockchain is kind of a committee right now, and the committee does some stuff. It's just like you don't want the committee to do like timing critical stuff or pick our winners and losers like directly, I think is my rant. But I am less bullish committees than many in the space, I won't lie.
Okay, and I guess you mentioned it, the multi-MEV boost meme, which I think Bert introduced, the idea that if you're running these external auctions for multiple proposers, is there not some incentive to run these in conjunction or run them all sort of atomically in a almost like a combinatorial auction kind of fashion, undermining a lot of the committee-based incentives?
Well, it's certainly an incentive to collude. I think if you're building a blockchain and you think that you have collusion, not just unilateral deviation, but actual collusion between more than F nodes that are Byzantine, then what are we doing? Like they could just double spend at that point. I think that's a graceful failure argument there that, hey, if we end up with a blockchain where more than F are faulty or more than F are Byzantine, then we'll go back to the proposer monopoly in that case. That's unfortunate. I'll go work on AI or something else. Because I'll give up. But like, I think there's also a bunch of honest parties in Ethereum who have incentives for the long-term health of the system. And right now they're running MEV-Boost. Like we run MEV-Boost at Consensus, right? Because our action in running MEV-Boost does not change the equilibrium of the whole system. Whereas if we were in a system where we're one of 8 proposers quite a good percentage of the time, or Coinbase is one of 8 proposers quite a good percentage of the time, their individual decision has the power to take us from a terrible equilibrium where we have proposer monopoly again and leave us in a good equilibrium where we have no proposer monopoly and we have apps functioning well. And that's my perspective on it, is basically now we have a one of one honest assumption, and that like one guy is not going to censor. And here we're going to have like kind of a one of n assumption, and that's better than one of one.
Ooh, I'm so triggered. I have this thing in my brain where like I can only think in nuance, and any sort of A or B, like immediately I'm like, so I think one interesting thing is you said like, look, if F are faulty in your blockchain, what are we even doing here? I totally disagree with that perspective. For example, in ETH, you could consider running MEV-Geth when Flashbots came out to being a faulty node. Certainly many protocol developers did. And we had almost 100% of the network being faulty and still providing like many of the guarantees that we care about. So I think it actually does, like in a rational world where everyone's incentive is to move in the same direction, we actually need to handle incentive perturbations like maximally against the set of properties we care about without this binary of like, are nodes faulty or are they honest? We need to look at like, what will they actually do in the protocol and what will they do as a herd? And do we still get the properties that we want out of the system?
So let me just say before you
quickly.
Okay. Like we're reasoning by analogy here. This is not the same as MEV-Boost. MEV-Boost was a unilateral decision that was a profitable deviation for everybody. And like I said, your decision did not change the decision of anybody else to participate. In Collude Boost, your decision does change the decision of other people to participate. And if one person in the quorum of 8 or of 4 or of 16 or however many proposals we have is honest, then they will not have Collude Boost because you need everybody participating. And one of the nice things about having 8 is that the probability that you have an honest person in there, even if the honest share is quite small, is pretty high because you have to do like, something to the n, where n is the number of proposers. And that's kind of your probability of having a quorum without an honest person.
I mean, I'm going to sidebar that whole argument because I don't think we have time for it, but I will say I was talking about MEV-Geth, not MEV-Boost. And there I think like it is actually like your profit from deviating is proportional to how many people deviate because the total percentage of block space that was being allocated by the mechanism like also matters to the profitability of each block. Like if you're making 2% of the network blocks through MEV-Geth, it's not going to really attract flow and it won't give that 2% like 2% of the profit as if 100% of people are using it. They'll get much less actually.
That's, I think, a lovely discussion and a lovely point to end on. So much more to, like every interaction in this debate has given us another research topic. So much to come back for next year. Yeah, thanks guys.
Thank you.
character, or what should I do?
That's a good question. I guess engineer will do. Okay.
Yeah. All right, we're going to start back up again. So our next session is going to kick off with our first speaker, Wana Barbu, who is an engineer at Automata.
Hi, everyone. I'm Wana, and I'm here. Is it work? No. Sorry.
Oh, looks like it's on. It's just not picking up.
Oh, good. Okay. So, hi everyone. I'm Wana, and I'm here to tell you about how to build how to do partial block building with TEs. So this talk requires basic knowledge about TEs. So in case this is the first time you hear about them, TEs stand for Trusted Execution Environments and are hardware enclaves whose memory is encrypted by the CPU. This prevents unauthorized party to pick or tamper with the execution of the applications that run inside the TE. So TEs provide confidentiality and integrity of execution. And we are able to verify that the TE is indeed genuine by running this process called remote attestation. Basically, during the remote attestation, we ask a TE to prove its identity that's linked all the way to the hardware manufacturer and provide some hashes over what firmware and applications is running. So I've been working on with TEs for slightly more than 3 years at Automata, where we're working towards making it easier to build and deploy TE applications. We have a TE AVS that brings crypto-economic security to a TE network. One use case for this AVS is a TE multi-prover, which is basically like a watchdog that ensures roll-up state transitions are correct. We also have some efforts in making attestation possible on chain. And we try to make it cheaper. So we have this decap attestation library. And we're planning to release an attestation SDK soon. And we also do TE compile, which is a way to ensure that the software that it's a form of reproducible builds, because it's very important to ensure that what runs in the TE is correct. Anyway, so about MEV Booty, it's a project that started at the Hacker House, and it became part of the first round of projects in the EigenLayer Research Fellowships. And I want to give a shout out to Kaido, who supported me with this work. So in order to talk about partial block building, we have to go back to proposer builder separation, or PBS. You've heard about this before, but just a reminder, PBS is a mechanism that separates the role of proposers, those who propose the blocks, and builders, those who build them. And it creates a marketplace for blocks to be created by builders, and proposers can opt in to pick a block from this marketplace instead of building one on their own. And the de facto implementation of PBS today is MEV Boost. A rough description of how it works: we have these multiple builders that each build their block and send it to a relayer. In this diagram, it's a single relayer, but there can be multiple relayers involved. Each relayer will pick the most profitable block based on the one submitted, and will send it to the MEV Boost, which is a sidecar that the proposer will run if it wants to use MEV Boost. If it wants to use PBS instead of creating a block on their own. And one goal of PBS was to decentralize the block building, but the reality is slightly different because proposers have the incentive to pick the most profitable blocks, and as you've seen previously as well, it's not that easy to build a profitable block, and mostly 90% of the blocks on the MEV-Boost market are built by two builders. This means that more than 80% of the entire Ethereum blocks are built by these two builders, which is not good for decentralization and censorship resistance. So the idea with partial block building is to involve the proposers as well in the creation of the block. So with partial block building, the builder will still create the top of the block, the TOB, but now we allow the proposers to also have an input in what gets included inside the block via the ROB, the rest of the block. The question becomes like, how should we combine this TOB and ROB? And of course, our answer is to use a TE. But before that, I want to go to another factor that influenced some decisions in our designs, the relayer. So the relayer is a trusted intermediary that facilitates the communication between the builder and the proposer. And it has to be trusted by the builder to not unbundle their block, and it has to be trusted by proposers to pick the most profitable block that's also valid. That limits the pool of players who become relayer to only a few, and these players have to have a good reputation. And this also leads to a bit of a centralization in terms of the relayer, like roughly 75% of the blocks are built by only are relayed by only two relayers. Here, green and white correspond to blocks route, and it's also worth mentioning that this relayer does the work pro bono. There's no incentive and nothing for the relayer to be gained. So we are also thinking of whether we can remove the relayer from the picture. Okay, so this is how MEV-Booty came to life. The idea is very simple. We leverage TEs to receive the TOBs from the builders and the ROB from the proposers. Then we combine this to create a block. And we have three designs which differ based on where the TE is run. So the first one is TE assembler, which is basically like the current MEV-Boost, just that the relayer is replaced by the TE assembler. Then we consider removing the relayer and running the TE at either the proposer or the builder. So we have the builder side TE8 and the proposer side TE8. So for the TE assembler, like I said, it's mostly like MEV-Boost. If you remove the ROB, like it becomes MEV-Boost. So the builders will send their TOBs to the TE assembler. The TE assembler will select the most profitable TOB, combine it with the ROB, and tada, it produces the block. And in case that the TOB and the ROB have conflicting transactions, the proposer can either ask the assembler to exclude TOBs that would conflict with the ROB, or you can ask the assembler, okay, you can remove the transactions from my ROB that conflict with the most profitable TOB. Then this is the builder side, the TE8. In this case, each builder will run its own TE8, and the proposer will connect directly to this TE8 and provide its ROB. Then each builder will combine the TOB and an ROB and will bid for the block. And the proposer, of course, will select the most profitable one. Due to the integrity guarantees provided by the TE, we can the proposer can rest assured that the TE8 will build a block according to the specification, so the builder will not be able to do anything malicious. And then in the case of proposer side T8, each builder connects directly to the T8 that runs on the proposer. This the T8 will assemble the block using the most profitable TOB that it received. And again, due to the confidentiality guarantees of the TE, the builder can rest assured that the T8 will not unbundle this block. Yeah, and another cool thing that we can do with MEV booty is that we can add the preconfs very easily. So preconfs is short for pre-confirmations, and they're basically credible commitments that a transaction will be included inside in a block before finality happens. Preconfs are used to provide timely execution guarantees and instant confirmations and so on to improve user experience. So I'm showing here how we can add preconfs to the T assembler. Basically, all we have to do is provide another interface that will allow users to submit their transactions. And now when the T assembler assembles a block, it will still use the most profitable TOB and the ROB, but at the end it can add the preconfs as well for the transactions that it pre-confirmed. There are more details, specifically like how we can do execution or inclusion, preconfs, and so on. We have a blog post coming soon that elaborates more on this topic. Okay, so to recap, current PBS is not ideal due to the centralization and censoring concerns, and basically proposers have to choose between the rewards or the ability to actually have a say in what gets included in the block. With partial block building, we aim to give some of this power back to the proposers, and thus enhance the centralization and censorship resistance. And by using a TE to do partial block buildings, we are able to minimize the trust assumptions and maybe even remove the relay from the picture. And if not, and we by doing this, we promote a more inclusive and resilient ecosystem, because now anyone with a TE can become a relayer. And I also showed how MEV booty can do preconfs. If you want to know more about what we are working on with TEs, you can follow us on X. And that's it from me. I'm happy to take any questions.
So I'm curious, with the idea that the sort of rest of block comes from the proposer, how you relate this design to the fossil proposals coming from the EF, where the proposer proposes, or like some validators propose a set of inclusion lists that the builder are confined to. I think the combination of fossil with some of the discussions around block builders running TEs might actually naturally bring people close to your design. And so I'm curious if you have thought about the differences between a world where we have like a TE block builder and fossil versus your design that's, I think, a bit more specific than just TE block builder in general.
I haven't really thought about this before, but I can see that it can easily be modified to allow multiple parties to input their ROB, basically their own inclusion list that will be after that included in the ROB.
And in your view, what is the most challenging, the biggest challenge to realizing this design that you put forward?
You mean MEV booty itself, or
yeah?
I think it's mostly an implementation.
But is it just hard to do the engineering, or are there specific challenges that you have to get over in the implementation?
So the way I tried to do the engineering was based on the current MEV boost, and because I wasn't very familiar with that, I ran into some issues, but it's mostly a skill issue on my part rather than engineering issues, I would say.
Okay, that's a familiar feeling. Thank you.
All right, any other questions?
Thank you.
All right, let's thank Juana.
All right.
All right. Our next speaker is James Austin, who is a PhD student at Cornell Tech.
Thanks. Okay, is this... Hello? It's working? Okay. You guys can hear me? Awesome. Yeah, so I'm going into my third year in my PhD. I'm part of Ari Jules' group here. And I'm going to talk about off-chain coordination with something called liquefaction. So the story starts with private keys, and private keys on blockchains represent ownership of assets. So if you have a private key, then you can transfer any assets that are associated with the public address. And because of this, if your key gets stolen, then sweeper bots can come in and steal your assets as soon as you try to send them. And because you don't want to share your key and have your assets stolen, you want to keep it secret. And because of all of this, we have this widespread assumption throughout blockchains that keys are held by single entities. So, you might have a person holding one key, you might have a person holding many keys, but in general, keys are held by a single entity because you don't want your assets taken from you. And because if you did want to collude with someone, you would need to trust them completely. And there are a lot of things in blockchains that kind of reinforce this assumption. So things like NFT profile pictures associated with your account, ENS domains, these kind of attach identity to your blockchain address. And then even when we're analyzing blockchains, we look at things like holder numbers, where there's kind of this implicit assumption that that's roughly correlated with the number of unique individuals holding some token. So we have all these assumptions about private keys. We have assumptions about the secrecy, that you don't share with anybody, and that some single entity controls it. And then we also have assumptions about ownership, meaning that if you see a transaction posted with an address that people have associated with you, then that means you must have sent that transaction. Similarly, if you have a message signed from an address associated with you, it means you must have consented to signing that message. And we see this all the time, even just like analyzing the blockchain. So if you look on Etherscan and you see transactions sent from Vitalik's address, then you assume that Vitalik consented to these transactions and sent them himself. So if you have a private key, you can sign any sort of message. But what we can do is we can use TEs to kind of change that. And we introduced this concept called key encumbrance, where the TE, you generate a private key inside it, and the TE will restrict which messages you can sign with that private key. So the TE might, for instance, let you sign almost any message, and it will enforce certain restrictions on what you can do with it. The most easy way that we found of kind of specifying these rules are just creating a smart contract. And this smart contract will run on a TE blockchain so that it has the privacy and confidentiality and integrity guarantees that you get with TEs. So the upshot here is that the TE enforced smart contract that generated this private key is now the owner of the key and can kind of do whatever it wants in terms of who is able to control the key. So For instance, you can now have a key that, say, Alice can sign certain messages for and Bob can sign other messages for. And Alice and Bob don't necessarily have to trust each other at all because they trust the TE will uphold its smart contract. So this actually breaks a ton of our assumptions about private keys that we generally have. So now keys can be held by multiple people who don't trust each other, and a message signed from an account that's associated with you might not have been from you. And same with transactions. It might have come from someone else that your encumbered key authorized. But what's really fascinating about this is the encumbrance that I talked about. This is completely invisible to the public blockchain. So you can do all of these shenanigans completely outside of Ethereum, and no one really even knows that you've done this. And the T's confidentiality guarantees, it kind of helps. You can kind of use that as a way to hide these agreements. Now, I'm not the first person to have studied this. Phil Dyan wrote a blog post about the rise of dark DAOs, that is, DAOs that are enable vote selling on DAOs. And then there's another one, a paper called Delegatee and some others that talk about ways of creating broker delegation in Web 2 accounts. Like, for instance, having an email address where you delegate access to some of your emails so that an assistant can help you manage them, something like that. So yeah, as I mentioned before, with key encumbrance, you can hide a lot of activity through that by just doing it off-chain. And with dark DAOs, again, this is trustworthy vote buying of systems which target DAOs, and they separate the ownership of the DAO tokens from the voting power that they confer. So in this example, you might have a vote buyer who wants to buy a bunch of DAO votes and swing a proposal, and this briber might specify some price he is willing to pay for buying votes. And then users with encumbered wallets will have had to enroll in some encumbrance policy, as we call it, prior to doing this. But the encumbrance policy will say, for each DAO proposal, you can choose. You can either vote on the proposal yourself and give yourself exclusive access to voting on it, or you can sell this exclusive access to voting on this proposal to somebody else, and you no longer have control over that vote from your own accounts. And so going back to this example, now the briber can reliably sell or can reliably buy votes from other people, and there's this fair exchange for the vote sellers are able to get the money, and the vote buyer is getting a guarantee that he'll be able to sign any vote he wants from these other accounts held by others. And this is completely dark, so you can't really show that, or you can't see from looking at the voting records whether any of this sort of collusion happened. And the T's will help make sure that this is kind of confidential. And incidentally, it's actually pretty easy to build these on TE blockchains, especially ones which are EVM based. So we ended up using Oasis Sapphire as our platform to build a dark DAO. And we just wrote everything in Solidity. So we have our code posted, and I'll have a link to it at the end. But it's actually not too difficult to build these because of the EVM framework. We also built a second type of dark DAO that makes use of what we call autonomous accounts. So these are accounts that are completely owned by a TE smart contract. There's really not a concept of any other person who owns each account. And that will completely manage all of the DAO vote selling and so on. So with autonomous accounts, you can more easily create derivative assets. And so we actually liquefied DAO votes using this system, wherein you will trade your DAO tokens for what we call a dark DAO token. And the dark DAO token, you can't vote for it in for the DAO using the dark DAO token, but the dark DAO will automatically sell all of the votes that its tokens hold to the highest bidder at every election. So it's kind of like liquid staking for DAO tokens. It will accumulate some bribe money over time, and you can swap it back for a DAO token plus the bribe money at any time. So there are other interesting things you can do with key encumbrance. You can hold your tokens in other people's wallets. And again, this is largely invisible, these agreements that happen. So you can even trade tokens with other people holding tokens in encumbered wallets. And again, this is invisible from Ethereum. An interesting thing you can do with this is you can fake theft. So since you can trade ownership of assets without kind of revealing any proof of this on Ethereum, you can collude with some entity that is known to drain wallets, and you can in your collusion you can get a guarantee that they will give you ownership of any funds that you send to them. Basically faking that your coins were stolen, although you still retain ownership of them afterward, probably for a fee. And then, of course, you can sell entire accounts because the TE has ownership of the key. So the TE can just kind of point who controls that key to somebody else. And you can, with this, you can kind of create markets for accounts that are presumed to be eligible for airdrops. And you don't even have to know what format the airdrop takes. You can just say that I want to buy this entire account, which I think will be eligible for some airdrop in the future. Now, there are a lot of other applications to key encumbrance that I'd like to say are targets of it that we need to be aware of in the future as encumbrance might become more widespread. The first is soul-bound tokens. So soul-bound tokens have this assumption that that the ownership of them can't be transferred to anyone else because of the single entity key ownership assumption. So you can't actually transfer soul-bound tokens to other addresses, but you can still sell your key or sell proofs of ownership of this key to somebody else. Pretty much breaking the purpose of soul-bound tokens, which are to be used as like a reputation token. And then also, quadratic voting is another big target. So the idea behind quadratic voting is that you have some amount of DAO tokens, and you might take the square root of that to get what voting power you get in order to make these DAOs that use quadratic voting a bit more decentralized, where it's not completely plutocratic. But the problem is you can just distribute your tokens with willing colluders. And in some cases, you can even get a square of your voting power because of the quadratic voting system. And the reason this is important is like this will bypass any identity mechanisms because your colluders might have passed those identity checks, and you can still collude with them to acquire that voting power. So NFTs are often used for like getting access to events in like live in person, but with key encumbrance, you can just sell your access rights to these events to other people, even though they don't actually own the NFT or whatever it is that gives them access. And as I mentioned before, like reputation can be sold. So if your account, your address has really good reputation, you can sell that to someone else who wants to have an account with good reputation. And again, as I mentioned before, airdrops. What's especially unique about airdrops is that when you sell accounts, you can actually de-risk airdrop farming because you can separate the airdrop farmer that does all the tasks to qualify for the airdrop from the entity that might be specialized in selling the airdrop token as soon as it launches. So if there's some if the airdrop has a particular hidden time when it launches, and there's a group that's specialized in selling all their accumulated airdrop tokens immediately, then this kind of helps separate the two and de-risk the farming. It's been proposed that some Uniswap v4 hooks will give discounts to holders of maybe like an NFT or like having specific pools that will benefit particular accounts. But with key encumbrance, you can kind of just sell access to your account and get around these restrictions. So another thing you can do is you can kind of do a group buy, where if you need some amount of reputation or some amount of coins to qualify for a discount, you can kind of collude with others to share just one account, and then you would just need 1 over n of the total required assets to maybe qualify for that. Privacy pools, interestingly, also have an application for key encumbrance. So with privacy pools, it's a privacy protocol that you can dissociate yourself from deposits that you don't want to associate yourself with. But what you can do with key encumbrance is you can encumber your key such that you're not allowed to sign proofs saying that you're dissociating from anyone else in your own set. So it's kind of like a completely private group that can't rat each other out in, which is pretty interesting. Now you might ask, like, what sort of countermeasures can we have toward key encumbrance? But most of them that you might think of, like measuring latency to sign transactions or something like that, they don't work because key encumbered wallets act just like hardware wallets. So a lot of the same things you might run into, like maybe making the message size super long. Well, not many hardware wallets can support super long messages when signing transactions. There is one way you can definitely break liquefaction, and that's by making transactions or messages indistinguishable from each other for the same application. But at the same time, this creates a security risk, because then when users are signing these messages or these transactions, they don't know which one they're signing, and hardware wallets can't really tell the difference either then. So we do have an actual countermeasure, and that's called complete knowledge. And proof of complete knowledge is essentially a proof that you couldn't have encumbered your key. And it basically shows that your key must have been leaked over some insecure channel. And we have a couple of ways of creating this type of proof. Mahimna will explain them at SBC on Thursday morning at 9 a.m. if you're interested. So we're currently in the process of writing a paper about how to liquefy everything using key encumbrance. But in the meantime, we have a couple links here. We have our dark DAO work, where we actually implemented complete dark DAOs and key encumbered wallets. And then we also wrote a paper about DAO decentralization. So feel free to check those out. And then I'll end with some discussion about Web 2 encumbrance. So Shin from Flashbots and Andrew Miller and Ryan and a couple others have been working on some encumbrance of Web 2 projects, which isn't as satisfying as Web 3, because the Web 2 service providers can kind of just change the backend interface at any time. But at the same time, this is pretty fascinating that they were able to do this. They were able to encumber a Twitter account, so you can send messages from it by purchasing an NFT or something. And then also they created a dark DAO within a strategy game called Mischief Plays Venmo. And that's that one. So thank you for listening, and stay tuned for more about encumbrance to come, and we'll have that paper hopefully complete or at least released in the next couple of months. Thank you.
All right, any questions for James?
Great talk, James. I really like the idea of faking your money being stolen. That was one I hadn't heard of before. I'm curious. I think this is a topic that comes up every time people talk about dark DAOs, but I haven't heard a convincing answer. Like, we've had the technology to do this for a while, and the incentives for like voting, collusion, these kind of things have obviously also been there, and yet we don't have any known large examples of this happening. Why do you think that we haven't seen more of it? And why do you think we will in future see more?
Yeah, so our classic answer to that is we don't think DAOs are that decentralized right now, where this would like actually become like a big factor. We think there's too much centralization where there are big players that aren't willing to collude. But as DAOs become more decentralized, we think that like dark DAOs are going to become more attractive because that would be kind of the only way of amassing lots of voting power, is actually getting lots of people on board and having assurance that they're going to work with you. Like right now, maybe some of the top players can kind of just get in some Telegram chat and say, we're going to do this, let's all do this together, and they kind of can swing the whole vote themselves. Was there another question? Okay.
Any other questions?
And I also will add that multi-signature wallets are kind of like a form of DAO. So I would say those are also pretty vulnerable and should be kept in mind too. Yeah.
All right, let's thank James.
Hello.
Our final speaker of the day will be Fan Zhang. Fan is a professor of computer science at Yale.
Welcome to the last talk of the day. The title of the talk is Using TEs Without Trusting Them. It's a clickbait. If you use TE, you're going to trust them somehow. So what I meant is, how do you use TE without trusting them completely? Okay, so what do I mean by that? Just a quick reminder, what is a TEE? TEE stands for Trusted Execution Environment. It's an isolated execution environment that protects the integrity and the confidentiality of a piece of program and the data, right from other software and hardware. Popular examples of TEs include the Intel SGX, PDX, and TEs from other manufacturers and the open source community as well. So the primary features are integrity and confidentiality, as well as the ability to attest to a third party, remote third party, that it is indeed a piece of code X running a genuine TE. And this attestation is it boils down to a signature by a key that is protected by the hardware. So the point of this slide is to say that the integrity and the confidentiality guarantees are not independent. So the integrity, the correctness of the attestation stems from the privacy or the confidentiality of the attestation key. Okay. These three features make TE a pretty powerful. Is this better? Okay. Good. Okay. All right. So yeah. So these three features make TE a pretty powerful tool. The mental model I'd like to think TE is to think of it as a trusted third party, but secured by the hardware. And having a trusted third party really is a very powerful thing, and it solves a whole bunch of problems that cryptography aims to solve. So there has been a lot of use cases in Web3. It's interesting that some of the applications were kind of they came out 5 or 6 years ago, early on, when shortly after the release of Ethereum. But recently, in the last year or so, there's quite a visible rekindled interest in TE. And this time around, I would say there's a lot of legitimately new applications, such as the use of TEs in MEV block builders, and others like one-time signatures implemented by TE, account encumbrances, as you have just heard from James, and even Web 2 accounts can be encumbered. And here, I think, just insert a quick link. The team encumbrances, just to drop this draft on how to encumber Web 2 accounts. Okay, so this all sounds good and well. There's a lot of exciting use cases of TEs, but just a small problem, right? TEs, as we know them, aren't perfect. TE SGX.fail is both a website and a paper. It's a great resource to learn about all the attacks that SGX have fallen to. There's more recent works that extend the survey, the scope of the survey to a broader range of TEs. So this table is taken from this recent SOK paper. Basically, you can see that almost all like widely available TEs have had some vulnerabilities. And almost all of the vulnerabilities broke the confidentiality guarantee, and quite a few of them even broke the integrity. You can see the check on the last column of the table. So that's what we know, right? That's the past. So if history tells us anything, then what should we take away from these attacks? I personally want to kind of advocate a pessimistic view here. I personally think TEs aren't and likely won't be perfectly secure. And of course, nothing will be perfectly secure, but building TE seems particularly hard with the tools we have today. Reasons include the strong adversary model, the complexity of the modern architecture, and just the way that TE is developed today, right? The closed source approach and so on. On the one hand, there's hope. There has been invaluable efforts towards so-called secure by design TEs, or open hardware TEs. But in this talk, I want to advocate that we probably should be prepared for TE breaches. And it is a hard technical question and a challenge to be able to systematically hedge against the risk of TE breaches. And that's the topic of the talk. The key question of the talk: how do we systematically hedge against the risk? How do we think about the risk? This is not the first time that this question was asked. There has been, roughly speaking, two schools of thoughts out there. Let me quickly summarize. First approach is to, you simply put less trust in TE. For example, the sealed glass proof paper proposed a model where you trust TE only for integrity, not for privacy. Right. This model is somewhat justified by empirical evidences because less attacks break integrity and more attacks break confidentiality. And the paper shows that even in that relaxed assumption about TEs, they are still pretty useful, and they essentially function as a form of zero knowledge proofs. Right. If ZKP is useful, then TE without any privacy is, roughly speaking, equally useful. Assuming there's integrity assumption is true. So that's trust less. A second approach is to trust the TE but keep detecting its failure. All right. So the example I can think of is the Sting framework. The rough idea is you inject crafted inputs to the TE, right? So that when there's leakage, you can not only detect the leakage but also use the injected inputs to help you prove the leakage to the public. Okay, And so this allows the upper level applications to handle TEE failures. I won't get into the details of these works. But in this talk, I'm going to give you, going to present two more ideas from our recent works. So, idea number one is sort of a kind of a an extension of the trustless approach. We find that in certain systems that are vulnerable to denial of service attacks, we could use TEs to prevent denial of service attacks, and the result is you have a system that relies on TE only for liveness, right? Not for security. While the second idea I'm going to talk about is essentially it leverages the detection of leakage, and it places the incentives so that the attacks are disincentivized using insurance and bug bounties and these economic leverages. Okay, so I will let me start with the first idea, and if time allows, I will talk about the second one as well. Okay, so the idea is we put forth this idea in a paper we called ZipNet. It's about making a kind of anonymous broadcast protocol called DCNets cheap with what we call distrusted execution environments. DCNets are a protocol, an anonymous broadcast protocol. So the purpose of such systems is to allow a group of people to broadcast messages to each other without revealing the sender's IP addresses. So it's a privacy-preserving communication primitive. It's important by its own, and it's also important component of bigger applications like privacy-preserving payments and pretty much any privacy-preserving systems that you want to preserve the network layer identity. Okay, so how do we build a DCNet? What are the trade-offs in available DCNet systems? DCNets are attractive for their strong anonymity properties, and in particular, they're not vulnerable to traffic analysis like Tor. And they are also attractive for the palatable trust assumptions. Modern DCNets usually are run by a group of servers. Users only need to trust that at least as long as one of the servers is honest, you enjoying this strong anonymity. So this trust assumption, so-called antitrust assumption, is rather palatable. Okay, the downside of DCNets in general is it's easily dosable by clients. Basically by sending malformed messages, the client can clobber the broadcaster channel. And prevention of denial of service attacks like these are usually, can be done with cryptography, but it is usually expensive and involves, multi-party computation or zero-knowledge proofs. So for that reason and for other reasons, existing DCNet systems, they are cheap on the client side, but they are expensive to run on the server side, right? So you need beefy machines to run, to handle the computation and the communication load. The problem is if it's hard, it's expensive to run these anonymity servers, then there won't be a lot of servers. And remember, the antitrust assumption says that, basically the confidence in the system scales with the number of servers you have. So if you don't have a lot of servers because they are very, very expensive, then the anonymity of the system is weakened. So that is the kind of the motivation why we care about making servers lightweight. Okay. So then in ZipNet, this system, we did a number of things to make a DCNet server cheap. Here, I will highlight the part related to TEs. As I said, the big part of the server computation is to prevent denial of service or detect denial of service. So our idea is let's put client code in a TE. Okay, so TE will run on the client side. So this requires the client to do more work, but TE will check the client message and only sign off on it if it's is well formed. Okay, so the nice thing about this setup is what would happen when TE is bridged, right? So the attacker now will be able to bypass the denial of service prevention mechanism and clobber the communication channel. But happily, right, message corruption is something that's visible, that can be detected. If you notice that, right, the channel is corrupted, then that means there's objective, observable signal that TEs are bridged. And most importantly, even if TEs are bridged, the core property anonymity is intact, because throughout this process, we use TE to speed up, the denial of service prevention mechanism. We never relied on anonymity. And because we can, tolerate this TE failures, some TE failures, we don't really need a bulletproof TE. So it can be something like SGX TDX, or even something software based. So the benefit of kind of putting this client-side verification in TE is first that it has this nice trust assumptions in terms of TEs. The result is a much simplified server algorithm and a much better performance at a low cost. So the server, according to our evaluation, the server is 4 times faster than state of the art at a fraction of the cost. That's because the server can, we don't need to do the expensive format verification at the server. So, but the takeaway I hope is that there's the way that we use TE in ZipNet, we think is a nice framework. When TE works, right, we are in the optimistic path of the system. Everything is well and fast. And when TE breaks, it doesn't really harm the core property, which is the anonymity here. And importantly, TE breach is visible, it's detectable, because it clobbers the network, the corruption can be detected, and this allows the handling of TE breaches. For example, the protocol can switch to a more expensive cryptographic denial of service prevention mechanisms until the TE is fixed. All right, so this may generalize to other protocols. Yeah. All right, so that's the first idea. I think, how much time do I have? Okay, plenty of time. So, right, so the first idea is, just to recap, when you design a system, trust the TE for less. In particular, in ZipNet, we trust it for liveness. The nice thing is that we don't rely on it for security, and plus liveness failures in this case can be detected. So these are the benefits of this trust model. So I'm going to now just briefly talk about the second idea, which is to set up incentives to disincentivize side channel attacks. So this idea is put forth in a paper entitled "The Crudity: Stick and Carrot Approach to Side Channels." The paper is forthcoming in AFT 24. This so-called stick and carrot, the name will, the motivation for the name will become clear shortly. This framework is useful for key management applications in TEs, like when you store a key in the TE, and for example, when you use TE to build the custodial wallets, or when you apply TEs to certificate authorities, where you use TE to protect the signing key of the certificate. So what is the key observation, right? The key observation is when it comes to side channel attacks, there are potentially two types of attackers that can mount side channel attacks. The first type is the service provider that operates and runs the TE. So the service provider, for example, the service provider of some custodial wallet service is the party that has root access to the TE, right? It's the owner of the cloud account, and therefore they can mount all sorts of side channel attacks, right? Because they have root access to the TE. Another class of the attackers are what we call remote attackers or outsider attackers. These attackers can only access the system through public-facing interface, through APIs or web interface. So these attackers can also potentially mount remote side channel attacks, but it's going to be a lot harder. So they need more time and the cost to exfiltrate keys. Then what's the observation? The observation is we can deal with two types of attackers differently. To disincentivize the service provider from attacking the TE, we force the service provider to set up an insurance that will automatically compensate the users if the keys are leaked. Right? You can envision a smart contract being set up that accepts proofs of leakage that automatically disperse a payment to the users who report a leakage. So the goal of this is so that the service provider, despite being a powerful attacker, does not benefit from the attacks. The second approach to deal with outsider attackers, the attacks by outsider attackers are going to be, slower. So we can apply a bug bounty to incentivize the attackers to kind of stop early. Right? By stop early, I mean the attacker will kind of rather not finish an attack, but just give up in the middle and in exchange for a partial rewards. For the partial keys that's stolen out of the system. In the interest of time, I will not go into the details, partly because this work will be presented at AFT, and I invite you to kind of keep an eye on the longer version of the presentation. So I will just quickly summarize. So the key question this talk asks is, what if we embrace the assumption or the view that TEs won't be perfectly secure? And how can we then systematically hedge against the TE breaches? So there are, of course, security best practices that you should follow, but when you design applications of TEs, how can you incorporate these risks from the get-go? I surveyed two schools of thoughts, and presented one idea in each category. They are, trustless and trust but detect failure. Right? Trust until failure is detected. So these are here are the links to the paper. With that, I will stop here and take any questions.
Any questions?
Hi, thanks for the talk, Fun. I have many questions, so maybe this will go into the break. But my first question is, for Intel TDX at least, availability is a non-goal because, the hypervisor can, for example, performance degrade VMs to, for example, bypass any mechanism that, the TD may take to, for example, I'm understanding like this is some sort of heartbeat mechanism to ensure that the TD is executing. Is that a fair assumption?
Right. Availability is not. It's a non-goal. Or availability is not. We don't assume TE has availability.
So when you say you're saying liveness is guaranteed, how is that different?
So we trust the TE for liveness. That means that if TE is not bridged and if TE is available, the system has liveness, right? If TE is bridged, the system loses liveness. Equally, if the TE become unavailable, the system also loses liveness. But the difference, I think, the reasons for losing liveness can be due to malicious activities and benign faults, and this can be dealt with in different ways. But the point is that no, we don't trust TE for liveness. We don't rely it on for liveness. What I meant is if TE breaches, only liveness is lost. Maybe there's a bit of tautology going on here. I hope you got what I meant.
So I have a follow-up to that. How do you detect when the TE has been breached?
Yeah, that's a good question. So this is the part where such ideas are a little bit application specific. So in the DCNet example, the effect of TE getting bridged is to have the channel being clobbered. So you could, when you send the message, you could attach a sort of a checksum. And when the checksum is messed up, that's how you detect the TE has been bridged.
So you're saying that there's no way for the TE to be breached without some channel being clobbered? Like these are both necessary and sufficient conditions.
Yes, because TEs will sign off on the messages. And if the messages is not signed off by TEs, it will not be incorporated to the channel.
See. And then are there other questions? But I have one more if there's no one else. So one approach to, I guess, achieving the same guarantees as TE is to essentially invert the trust assumptions. So in TEs, you do not trust everything but the application. The alternative approach is to trust everything but the application, such that the application does not get corrupted. And so technologies like TPM and TXT are ways where you can trust your operating system, your firmware, BIOS, etc. How would you say like this would differ in terms of hedging against system breaches, I would say?
That's a good question. I haven't thought much about it. To me, that seems like a difference in the size of the TCB, like how big is your TCB? But the size is a little bit hard to say because some code are more maybe battle tested than others. I think generally this at the high level the framework wouldn't change because there still is a concern of breaches, whether in system code or application code. And such frameworks can still apply. But I'd like to think more about this question.
Good. Thank you so much.
Of course.
All right, let's thank our speaker. So that concludes the MEV workshop. Thank you all so much for coming and participating, and we hope we will see you again next year.